have checked that your TriCast is set correctly to record, yeah? You did check that this morning. We changed loads of settings to get all the cameras to work yesterday. You have checked the settings for recording the TriCast. You're recording on a TriCaster, yeah? So you've checked that it's actually recording? Wow.
Ladies and gentlemen, please take your seats. Our program is about to begin.
Ladies and gentlemen, our program is about to begin. Please silence your cell phones or place them on vibrate.
Good morning. If you could please take your seats, we're about to start. I would like to start today's event by welcoming our President, Tony Chan.
Good morning, Salam Alaikum. Your Royal Highnesses, His Excellencies, distinguished guests, and friends. Welcome to the KAUST Research Open Week. The Research Open Week is about showcasing the excellent science and engineering taking place at KAUST, first, as an international forum for conversation amongst our community of scholars, but beyond that, also as an opportunity for cross-learning with the rest of the university. This inaugural event was inspired by the launch last year of the KAUST Circular Carbon Initiative, almost the same date. I would like to thank our speakers and guests from near and far for accepting our invitation to take part in this research week. I would also like to thank our Vice President of Research, Professor Donald Bradley, our faculty and staff, as well as our contractual support teams for preparing this week's activity. Let's give them a big hand. Now, the theme of the Research Open Week this year, as you'll notice when you're walking in, is sustainability, which is a topic that is very much on my mind lately. You will have plenty of opportunity to hear and see our presentation of the research going on in sustainability this week. So I would like to devote the rest of my remarks today to share with you how I view sustainability more broadly. Humanity is losing our sustainability battles on many fronts. Many years of efforts inspired by the Brundtland Report and the UN Sustainability Development Goals has not resulted in meeting these goals. The 26th Conference of Parties, COP26, held in Glasgow just a few weeks ago, fell short of securing enough commitments from countries to keep global warming to below the target of 1.5 degrees above post-industrial levels. This failure is remarkable because it would seem that we would rather face a future of higher heat wave frequencies and hence risks of flooding and drought, coastal inundation, coral demise, and extreme weather than to step up our climate efforts today. KAUST sent 15 of our faculty members and staff, with 7 of them as expert speakers in multiple panels at COP26. Professor Johan Rockström, a member of our Climate and Livability Initiative Advisory Committee, perhaps summed it up best while there. Quote, "After Glasgow, we are no longer on a path of disaster, but one of great danger," end quote. We are still reeling from the effects of a black swan pandemic, with no clear path to preventing the next one, and emerging health challenges are predictably just around the corner. I can go on, but you get the idea. Sustainability, climate, and biodiversity challenges are looming large, but our actions are far from commensurate. During my keynote address at the Future Investment Initiative in Riyadh last month, my message was rather simple. Universities can no longer limit itself to its traditional role of education, research, and innovation. The challenges that I just laid out show that the window of time for action is narrow and closing, and the scale of response needed requires the whole of society to take action. The last time I checked, universities are part of society. Saudi Arabia has pledged to reach net zero by 2060, and it is incumbent upon KAUST as a leading institution of technology in the country to help show the way. KAUST will be net zero before 2060, and just how soon is a matter of ongoing careful deliberations, so please stay tuned. Our plan will include renewable energy deployment, energy efficiency, carbon capture, water and wastewater management, marine and coastal protection, revegetation of marginal lands, and also community programs. As a major partner of the Ministry of Energy in the Circular Carbon Economy National Program, KAUST is developing the tools required to help cut down carbon dioxide emission and also capturing the carbon. Beyond developing the tools, KAUST is piloting and upscaling their deployment. As a knowledge partner of the Saudi Green Initiative, KAUST will work with MIWA and the National Center for Development of Vegetation Cover and Combating Desertification in engineering large-scale ecosystems that are sustainable and will improve vegetation over and prevent the desertification. Research universities are truly unique institutions in that our main products are normally knowledge and people. However, the sustainability challenges before us are so urgent and formidable that KAUST is working with the Kingdom to take action. Let me close by calling attention to another ace in the hand of KAUST in our drive towards sustainability. A couple of months ago, I laid out our sustainability agenda to our Students for Sustainability group here at KAUST. It was a virtual gathering, but I can feel the energy in that virtual room. Last month, I saw our students again, this time leading other institutions in the Kingdom in a discussion of carbon dioxide emission reduction options during the youth segment of the Saudi Green Initiative launch. All these reminded me of the fact that universities are home to these agents of change, that is, our students. These students are full of passion, energy, and ideas, and they have grown tired of adults who are long on words but short on action. They see their future increasingly fraught with danger, with the window of time for action closing down in front of their own very eyes. Let us mobilize this impatience into increasing the ambition and shortening the time frame of our immediate action on sustainability. Let us act with resolve and be fully accountable to them. Thank you and enjoy the week.
Would like to welcome our Vice President for Research, Professor Bradley, on stage, please.
Thank you, Professor Chan, for your inspiring words. Assalamu alaikum, good morning to everyone here and online in the Kingdom and the region. Also, good afternoon and good evening to those who are joining us from around the world. As the Vice President for Research, I'm delighted to have the chance to welcome you all to the first ever KAUST Research Open Week. The theme for this week is Sustainability, Science for the Future. It's a topic that resonates with global initiatives to address the world's greatest challenges. These challenges are all too evident in the major transitions that are taking place in our climate and in energy, water, the environment, food and health, and the digital domain. We've put together what we hope will be an exciting program to showcase the research that is happening at KAUST within our divisions, research centers, and core labs, together with its translation to application through industrial collaborations, innovation, and startup activities. Throughout the week, you'll be able to join a fascinating mix of presentations and events that are taking place across the whole of KAUST. We're delighted to have an excellent slate of keynote speakers and panelists from as far afield as Hawaii and Iceland and as close to home as Jeddah. They will speak to a wide range of topics spanning medical innovation, coral reef conservation and restoration, the future of semiconductors, sustainable plastics, quantum technologies, women in STEM, artificial intelligence, green business, underwater robotics, Formula One motorsports, energy transitions, and the circular carbon economy. In addition, we have KAUST faculty talks on very timely research topics. We have a whole series of school science experiments along our spine. We have e-posters and early career researcher networking events in the library, a science and technology showcase exhibition, which is taking place next door in Building 19, and a startup showcase here in Building 20. There will be open house visits to all 12 of our research centers, to the KAUST Smart House, and to the core labs, and a behind-the-scenes look at research operations, innovation activities, and some of the many sustainability projects that's taking place within KAUST as it operates both as a university and a residential community. On Tuesday, we're delighted to host the launch ceremony for the Saudi Youth for Sustainability Association, and at the end of the week, as a wonderful finale, we will be joined by members of the McLaren racing team who will be taking part in the Jeddah Grand Prix a week from today. The McLaren attendees will also include STEM ambassadors who will support some of our school and student-focused activities, adding another facet to an outstanding partnership that we have developed together over the last 3 years. A pleasurable part of giving these opening remarks is to thank all of the people from across the whole of KAUST who have helped put together everything for this inaugural Research Open Week. I'd particularly like to thank all of the members of the Office for the Vice President for Research, the team that have been involved in helping us put everything together, including my executive assistant, Pauline Nolan. Countless hours have been spent on getting this project ready for today's launch. And finally, I'd like to record my special thanks to Dr. Nadia Karim from the Research Planning and Partnerships team for her leadership in coordinating this event. So I stay put because I'm also introducing the first speaker. So our first keynote speaker, Professor Christopher Ballentine, holds the chair of geochemistry and is head of the Department of Earth Sciences at the University of Oxford. He gained his PhD in isotope geochemistry at the University of Cambridge in 1992 and subsequently held research positions at the Paul Scherrer Institute, the University of Michigan, and ETH in Zurich. He then moved to the University of Manchester, where he held faculty positions for more than a decade prior to joining Oxford in 2013. Chris has worked with ExxonMobil, with Statoil and Total, as well as with the UK, European Union and US governments. He is a fellow of both the American Geophysical Union and the Canadian Institute for Advanced Research, and has served as the president of the European Union of Geochemistry. His research has further been recognized through an ENnie Award and the Geological Society of London's Bigsby Medal. Chris is well known for his work on identifying naturally occurring sources of helium, another gas in great demand, and also for his studies of the biogeochemistry that can occur when CO2 is sequestered in depleted oil and gas reservoirs. Chris will talk today about his recent research on the occurrence and potential for commercial extraction of natural, so-called gold hydrogen. The amount of hydrogen that is generated in natural crustal processes is significant, and the challenge is to identify where such hydrogen might be accessible in sufficient concentration to permit its efficient collection and use. Please join me in welcoming Chris.
Well, thank you, Donal, for that kind introduction, and I'd like to thank Donal, Tony, and all of the team for both inviting me and the warm welcome I've had since arriving. It's really fantastic to be at KAUST, and what a great place it is to be giving a talk, particularly on this inaugural Open Week event. Let me find my talk. So I'm going to be talking about hydrogen, and very appropriate given that today's topic is water. I think everybody's aware that if we want a sustainable environment globally, we need to make the transition in our energy use to clean energy, and what is cleaner than burning hydrogen, where the only product is energy and water. Before I move on to my talk, I do want to acknowledge my colleagues, my senior colleagues, John Gluyas at the University of Durham, Barbara Sherwood-Lolla at the University of Toronto, but also acknowledge our joint research teams. No one does research without a substantial input from young, bright, enthusiastic scientists, and we're no exception. We have a great team supporting us, from PhD students through to senior research fellows. Hydrogen, it's not just a source of energy, a source of clean energy, but it is so much more. Hydrogen has the potential to be the principal stock for generating synthetic hydrocarbons, if we want to generate biofuels, for example. And also, it's a key component using the Haber-Bosch synthesis to generate fertilizers. So ammonia is one of the principal sources of fertilization. So understanding how we can generate hydrogen cheaply, the sources of hydrogen, not just for energy, but for a whole host of uses. Hydrogen is going to be a key component in that energy transition. When talking about hydrogen, you will often hear different colors assigned to it. We can generate hydrogen from fossil fuels, and if we generate it from fossil fuels, there's a byproduct, and carbon dioxide is a byproduct. If we don't put the carbon dioxide back into the ground, then it's not really helping us at all, and that's called gray hydrogen. Blue hydrogen, that's where we want to be. If we generate hydrogen from methane reformation processes, for example, where you add steam and methane, you can generate hydrogen and carbon dioxide, which, if you bury, we call that hydrogen blue hydrogen. And green hydrogen getting better if we have the a green source of power through electricity, perhaps using wind, solar, hydropower, or nuclear, we can use that electricity to separate the hydrogen from water, generating, again, a clean source of hydrogen. And we call that green hydrogen. The costs of each of those are changing. Blue hydrogen has a cost range depending on the local conditions. Green hydrogen, the cost is fairly high at the moment, but estimates are that as this scales up and moves into production, those prices will drop and be equivalent to grey hydrogen, which is producing hydrogen from hydrocarbons without the cost of burial. But green hydrogen's not without its challenges, and one of the key challenges is that at the moment you need fresh water to separate hydrogen. You can't take saline water and simply separate hydrogen from it. And typically where you have solar energy, water, fresh water resources can be a challenge. So I'm talking today about natural hydrogen. There is hydrogen produced naturally, and I'm going to talk about its sources and the amounts. But is it possible that there is a source of hydrogen that is commercially viable, that has a cost-price point that matches or could even be better than green hydrogen? And that's going to be the focus of my talk today. It's a work in progress, but I think there's certainly some promise for this source of hydrogen to be a component of that energy mix for a green future. Our journey starts in 1977. It's not that long ago, certainly in geological terms, but in science terms. In 1977, we found the very first black smokers. These are hydrothermal vents on the seafloor, and these are engines. These are powerhouses in the oceans. We've 65,000 kilometer volcanoes sitting at the bottom of the oceans, connected, and at points on those mid-ocean ridges, we have hydrothermal circulation where we're sucking in the seawater, and that seawater is reacting with the rock and bringing to the surface in these plumes, which give them their name. These black. It looks like this is black smoke coming from them. This is hot water containing hydrogen, methane, and many elements that the water has extracted from that rock interaction. It's the hydrogen clearly that we're interested in, and this is produced by a reaction called serpentinization. Iron-rich minerals, peridot is one of those. Iron-rich minerals will react with the water, and the magnesium in those rocks will produce elements that we're not so interested in, but the iron in these minerals reacts to form molecular hydrogen. That molecular hydrogen in turn can react, which will generate some of the methane we also see in these plumes. But the first indication that we have a significant source of hydrogen generated naturally by geological processes from simply water and rock. So where else in the world do we find these iron-rich rocks? And the answer is everywhere. 70% of the continental crust contains iron-rich rock. So we're looking at a geological period from the Precambrian, so rocks older than 540 million years ago form 70% of the continental crust, and these rocks are dominantly iron-rich, very similar in composition to the oceanic crust, where those black smokers are generating that vast amount of hydrogen. I quite like this figure because this, particularly given that water is the conference topic for today, this places in context the amount of water on our planet. We can see that if we take the entire surface water of our planet and just put that into a ball, take it out of our oceans, that places a perspective on what the amount of water on our planet looks like. You might not be able to see it very clearly, but there's a tiny little spot just about here, which represents our entire fresh surface water, just 93,000 cubic kilometers of water. Far bigger resource of water is fresh groundwater sitting in the ground in large aquifers. We're looking at just over 10 million cubic kilometers of water. But of relevance to this talk, there is an equivalent amount of water, which is saline, and that water is sitting in this iron-rich rock. So we've got the perfect conditions for the iron-rich rock in our continental crust to react with a very large amount of saline water, which is naturally sitting in these in the continental systems. There are differences, though. This engine, which is the mid-ocean ridges, which is driving these black smokers and the hydrogen in these black smokers, it's hot, it's active. There's a large amount of water being actively pulled down and flushed through those rocks. The iron content of the oceanic crust is also very high. That combination means that the reaction efficiency is very high. We can generate a lot of hydrogen very quickly from the reaction of seawater with the oceanic crust, even though the circulation of the water is not so deep. So, very different to the continental crust. The continental crust is cooler. The iron content isn't so high. We've got more to play with. We've got a lot more to play with. The continental crust mass is about 100 times that of the oceanic crust. So we've got this mass, which is in our favor, but the reaction rates and the reaction efficiency is much less. As we go down into depth, the porosity decreases, the amount of water the rock has to react with decreases. So we're looking at about 100 times less reaction efficiency in the continental crust. But we can calculate it. But it is 100 times slower than the reactions that are occurring in the mid-ocean ridges. Because it's 100 times slower, it means that another mechanism of producing hydrogen becomes viable, becomes important to consider. And that's the natural radioactivity that occurs in our continental crust. Within our rocks, we've got uranium and thorium and potassium, which are naturally occurring at parts per million levels. They're naturally generating small amounts of ionizing radiation, which splits water into hydrogen and oxygen. We have it's quite a complex process where we split hydrogen and oxygen from the water. There's a series of radical reactions, but one of those end stable products, again, is hydrogen. It occurs at a very slow rate, but because the continental crust is massive and time is on our side, it turns out that this is also a significant source of natural hydrogen within the continental crustal system. So we looked at this a few years ago. We published our work on this back in 2014, where we looked at the range of reactions, the reaction rates, and where it's occurring in the continental crust, and showed that with that leverage of volume, the continental crust is so huge, so large, it's actually producing as much hydrogen as the mid-ocean ridges, even though it's cooler, even though the reaction processes are less efficient. But there is a big difference. The oceanic crust is continually being made and destroyed. It's very rare to find oceanic crust actually older than 100 million years in age, because it's continually being made, processed, and subducted. In contrast, the continental crust is over 2 billion years in age in many places. The continental crust has had 2 billion years to generate hydrogen. The question is, where has that hydrogen gone? Has that hydrogen just leaked out? Is it still sitting down there and inaccessible? Or is there something in between where it's escaping, being trapped, concentrated, and is it accessible? So we have a summary of that in terms of the generation rate. Moles of hydrogen, large number, it doesn't really mean anything. I wanted to put that into context. We've been generating this for billions of years. In 1 billion years, the continental crust generates the equivalent of 170,000 years of present-day oil production in terms of its energy potential. If you burn 1 billion years of the continental crust hydrogen, that is the equivalent of the energy released by 170,000 years of present-day oil production. So I've invented, well, I'm not sure I've invented it, but I'm sure other people use it, but present-day oil production is a useful reference unit to convert these units of moles of hydrogen per year. It's not all great news if we want to find natural hydrogen, because natural hydrogen is reactive. There are reaction routes which naturally occur in the continental crust. There's a Fischer-Tropsch synthesis, which chemical engineers have used for decades, where if you add hydrogen, carbon monoxide, catalyst, put that at pressure and temperature, you can convert that hydrogen into higher hydrocarbons. And it's quite clear from looking at natural analogues that process is occurring in the continental crust. Hydrogen generated through natural production can generate through the Fischer-Tropsch-like processes higher hydrocarbon chains, and that will destroy some of that hydrogen which is generated through those water-rock interactions. Hydrogen is also bioavailable. Microbes living in the shallow crust are looking for energy sources. Hydrogen has got that energy source. This is a microbe called Hydrogenobacter thermophilus. It's a microbe that's able to survive to high temperatures, but it uses hydrogen as an energy source and as a waste product generates methane. So these are sinks. These are mechanisms where natural hydrogen is being used up within the continental crust. So we've got questions to ask. What is the preservation of the hydrogen on geological timescales? Are those processes destroying it completely? If not, what are the mechanisms that control release of the hydrogen from the deep crust? What are the rates of release? It's no good just releasing the hydrogen from the deep crust without a mechanism to bring it to a point where it's focused and concentrated and exploitable. So do we form a gas phase which will do just that job for us? Are there trapping structures within the geological system capable of holding hydrogen? Hydrogen is very diffusive. It will diffuse through many rocks. And having brought it to the near surface, those hydrogen sinks are still active, and in particular microbial activity. Are we preserving the hydrogen once we've brought it to the surface? So we can look at this. We have got access to the deep continental crust through boreholes, but also mines. This is an example from Canada. We're looking at a massive volcanogenic sulfide deposit. It's a giant zinc mine. This is what the zinc mine, this thumbnail is what the zinc mine looks at the surface. Once all of the zinc ore had been pulled out of that, they've since been burrowing down, following the ore body, and they're now at a depth of about 3 kilometers. We can go into this hydrogen source rock and look at it in detail and find out what's happening. So this is a video showing sample collection. That might run in just a minute. But what we have are fracture fluids, and those fluids are rich in brine and rich in gas, and we can collect those. We can pass those through. We collect them in very simple materials. We collect them in copper tubes, collect the brine separately, we collect the gas separately, and we can analyze these fluids. And in just a second, you'll see how much water and gas there are in some of these mines. And this is the pretty noisy, grim environments. But just at the end of this video, you'll see down the corridor abundant water and gas flowing out of these fractures within the rock. These fractures within the rock are what accumulate hydrogen, methane produced from these other reactions, helium, and I'll talk more about the helium generated as a byproduct of those radiolytic reactions, which are also generating hydrogen, and other associated gases such as nitrogen. The key thing is we know the relationship between hydrogen and helium. We know the rate at which they're both produced, and we can look at the helium to hydrogen ratio, and if that ratio is about what we would predict, that tells us the hydrogen is not being significantly removed from the system. If the hydrogen is being removed, that ratio is going to change. In many of the systems we're looking at, it has changed, but not very much. That tells us the hydrogen is being preserved in these source rocks on geological timescales. And when I talk about geological timescales, I'm talking about hundreds of millions to billions of years. We can look at the radioactive decay laws. We understand how much helium is produced as a function of time from the decay of uranium and thorium. And we can look at the amount of helium that is accumulated within these fracture fluids. And that allows us to place some age constraints on how long that fluid, including the hydrogen, has been trapped within that rock. And these are results from several studies in the Canadian continental crust, the Kidd Creek mine, which I showed you earlier, but also from Sudbury, a nearby system. And we're looking at fluid ages up to 2 billion years in age. These fluids have sat there for 2 billion years without significant loss of their fluids. The rocks are 2.7 billion years in age, so it's not a completely tight system. If it was completely tight and hydrogen stayed there, it wouldn't be of much interest to us. Hydrogen is escaping from these rocks, and it's escaping to the surface. Because when hydrogen reaches the surface, it's often reacted out, it's often lost, we can switch our focus to looking at helium as a proxy for what the hydrogen is doing. And that's what I'm going to do for the next few slides. Helium and hydrogen are both produced dispersed within the rocks. They undergo the same processes of release. The processes that control their transport to the surface will be the same. And the focusing mechanisms of that gas, the way the gas is focused and brought to commercially exploitable forms will be the same. And helium, like hydrogen, is also a very diffusive, very mobile gas. Hydrogen is not conservative, but we can use the helium as a proxy to understand what is controlling that gas production from the deep continental crust. An indication of what's controlling it is Yellowstone. Yellowstone is a big volcanic plume underneath the continental crust in North America. The continental crust has been point heated by this hot jet of rock, which is coming from the deep mantle, producing a lot of surface hydrothermal features. But if you measure the volcanic gases, they're also very rich in helium, which has been built up within the crustal system. And we can calculate how much helium is coming out. And if you could stick a plastic bag over Yellowstone, and you could hold that plastic bag over there for 1 million years, you would be able to supply the entire world's need for helium for 2 to 3 years. So just that one spot on our planet is releasing a vast amount of those gases which have been built up within the continental crust. This is telling us that, perhaps not surprisingly, if you've got volcanic activity, that is a mechanism to release these stored gases. And we can see that as a crustal flux of helium, and hydrogen will do exactly the same, as we move to volcanic regions, we move and change the efficiency of that release by up to an order of magnitude. We can have an enhanced helium deep gas release enhanced by up to an order of magnitude through volcanic activity. Volcanic activity is not without its issues because it also comes with volcanic gases. If you want to find where those deep gases are best exploited, close to the volcanic center, it's not particularly interesting because in this case, the helium is diluted from percent levels to ppm levels by the volcanic carbon dioxide. As you move away from the volcanic center, you move to a Goldilocks zone where the heating is occurring, the volcanic gas isn't present, and suddenly the crustal gas jumps to 1 to 2% helium. The volcanic gas is gone. This is also where we would look for hydrogen. We see this same process occurring in other places around the world, and although I'm talking about hydrogen, helium is a gas which is in short supply, and we've been consulting with industry on where to find helium. And helium occurrence in Tanzania is particularly interesting because we have that combination of a volcanic system. The African plate is drifting apart. As it spreads, volcanoes are formed down the entire East African rift, and that volcanic heating is releasing hydrogen and helium from the deep continental crust. And at the surface, these are colleagues of mine, at the surface, you can't see them very well, but there are bubbles of gas which are coming out of the ground, which are 10% by volume helium. When they reach the surface, the hydrogen is gone. But if there's helium there, the hydrogen will have been produced as well. So we're starting to understand what happens to accelerate the release of gases, but helium and hydrogen are being generated constantly in the bulk of the continental crust where there isn't volcanic heating. And we can understand how the hydrogen is released from that portion of the crust by going to sedimentary basins which are in stable parts of the continental system. I'm moving now to the Williston Basin in North America. Significant oil-bearing basin. If you go down beneath the oil systems into the deep sediments, we find naturally occurring hydrogen, helium, and nitrogen primary gases without methane or hydrocarbons. So we want to understand that. We were able to sample natural gases throughout the sedimentary sequence. From the natural gases, we can look for water proxies, we can calculate the helium concentration in the groundwater, and we can start to generate an understanding of how the helium is diffusing from the continental crust through the sedimentary system and into the different layers of groundwater that form within that sedimentary basin. Clearly don't want to go into the details of the model, but the model that we've generated is from first principles. We can look at how the sedimentary system builds up slowly and what controls the helium and hydrogen concentration as the sedimentary basin is formed over about 450 million years. The key component is that these fairly simple-minded models fit very well the data. This is the higher concentrations that we have are completely consistent with a flux of helium into the base of the sedimentary system, and we can calibrate that flux from the concentration within the groundwater. Some of the groundwaters are below what our model would predict, simply explained because we have lateral flow of water, and we also have a lot of anthropogenic injection of water into the systems that we're sampling. We can calibrate from this approach the flux into the basins. The flux into the basins tells us that the amount of helium arriving at the base of our sedimentary system is equal to the amount of helium being generated in the continental crust, which tells us we've got something called steady state. The amount of helium in the continental crust is built up to a point where the rate at which it is being generated is the rate at which it's being released into the sedimentary system. Hydrogen will be doing exactly the same. We know from the helium proxy how hydrogen is behaving. So if we know how much hydrogen is being produced in the continental crust, we know it's being released at steady state, we can consider a general case of how much hydrogen is being released into a generic sedimentary basin system. We can take a 500 million-year-old generic sedimentary system. Fairly large basin would be 150,000 square kilometers, which is about 0.1% of the continental crust area. It's a trivial calculation, but a basin that's 500 million years old with that lateral extent would have received the equivalent in energy of 85 years of present-day oil production in terms of the energy that hydrogen would release. If present-day oil production doesn't mean too much and money is more important, well, one present-day oil production value that you can pull off the web is $1.7 trillion worth of hydrogen has moved through that sedimentary system. Sounds great, it comes with caveats. At this point, no gas phase is being formed, and the basin sediments are losing the hydrogen as fast as it's moving in. So what stops it? What generates the gas? Nitrogen is also generated in the subsurface. Small amounts of nitrogen have the capability to saturate the groundwater. If this is our sedimentary system, the nitrogen concentration as a function of time will increase as we put more and more hydrogen, more and more nitrogen into the base of our sedimentary system. Let me refocus on these dashed, these hatched lines are the nitrogen solubility limit. We cannot drive the concentration of nitrogen in the water beyond these dashes because we reach the solubility limit and we form a gas phase. As soon as we form a gas phase, all of the helium dissolved in the water moves into the gas phase. All of the hydrogen dissolved into the water moves into the gas phase. And the models become a little bit more complicated, taking into account these solubility limits. But what you can see is that we predict for the Williston Basin, this basin that I was using as my example, where we've got the data sets to calibrate the flux, we show that we would predict that in the deepest basal system, so this is the sedimentary system sitting just above that crystalline continental crust, we show that we would predict that the nitrogen solubility is exceeded. We would predict that helium will preferentially migrate into the gas phase, the hydrogen would move into the gas phase, and we can predict at what concentrations and ratios that would be distinctive, so characteristic of that process. And we find that. In the Williston Basin, in the Deadwood, there are primary helium and nitrogen reservoirs. We've not looked at the hydrogen in detail, but the helium and the nitrogen give us the characteristic helium to nitrogen ratio that we would predict from this process for forming a primary gas phase. I'm afraid this movie didn't load properly. That was my fault. But if this movie was running, I would be showing how that changes through time. And what we can do with this modeling process is predict at what time in the geological period that gas phase would start forming. And it's about 150 million years ago. The gas phase first forms that nitrogen saturation limit is reached 150 million years ago, which means from that point, we've got a mechanism to start accumulating the hydrogen. So we've reduced the potential hydrogen amount from 80 or so to 25, but still the potential for a massive amount of hydrogen progressing through that system while a gas phase is present. But for the Williston Basin, we also know that the rock types are not great for trapping helium. They're therefore not great for trapping hydrogen, because while we're forming a gas phase, there's still a significant amount of diffusive loss through that sedimentary basin system. So we need to look for sedimentary basin systems which have got better rock types, better trapping capability, more efficient ways of preserving some of that very large amount of hydrogen that is naturally produced and is escaping from the deep continental crust. This is a study that we're publishing at the moment from the Paradox Basin, again in the United States, in the Four Corners region, crossing between Colorado and Utah. It's a sedimentary basin system. Why it's interesting is because sitting close to the base of those sediments is a huge deposit of anhydrite. It's an evaporite. So this is an ancient sea which has evaporated, and all of the dissolved constituents have formed a mixture of gypsum, anhydrite, and salt to form a really, really tight rock. A rock which we don't think would allow very much diffusion through it. So we can test that hypothesis by looking at the helium. We can look at the helium content below the Paradox evaporite formation and the helium content above that formation, and from our modeling approach, calibrate the amount of helium that is getting through that system. So this is moving back to those models again, where we've got these estimates of observations, measurements of the helium in the groundwater above the Paradox formation. We've actually got samples from within the Paradox formation and samples from below the Paradox formation. Critically, what we show from this study is that this particular type of rock and thickness of rock is a very effective barrier for diffusion. We see no evidence of any deep diffusion in the shallow sedimentary system. And even within the Paradox formation itself, we see no evidence of deeper gas input. As soon as we're into the deeper sediments, we see evidence for a significant basement flux into the basement. So it's happening. That gas is being degassed from the crust into the base of these sediments, but it's not getting through this great big barrier, this natural barrier that nature has put in place. It's not a place to look for hydrogen, though, because we also know that these lower sedimentary formations, if you follow those to the edge of the basin, they crop up at the surface, and that allows water into these, and recent water also flushes through and destroys the ability of this particular basin to accumulate big quantities over the geological times you would need for hydrogen exploration. So I've talked about chemical sinks of hydrogen. I've talked about biological sinks of hydrogen. I've talked about the ability of rocks to trap hydrogen. We also need the quiet, geologically quiet, in other words, no flushing of fluids through our systems. So we're starting to build up a really good understanding of the different parameters that we need to develop an exploration strategy for hydrogen, the hydrogen which is certainly down there. Just conscious of time, I don't want to dwell too long, but we are looking to understand, once hydrogen has reached trapping environments, what happens to it. We're looking at surface seeps in South Africa. In South Africa, we have in the Free State, near Dryfontein, Bloemfontein, we have a lot of exploration boreholes into the crystalline basement, or rather into the sedimentary system, which strike helium. There's methane present, there's nitrogen present, but the hydrogen is gone. And we can apply various statistical approaches to understanding the environment in which those gases is produced, and ask the question about the origin of that methane. Is that methane from hydrocarbon source rocks, or is that methane from the degradation of the hydrogen that would have been produced? And there's some points on the screen, but the consistency of those points is completely consistent with the hypothesis that that methane, which we're now seeing at the surface in South Africa, is due to the complete loss of hydrogen, probably through bacterial action on that particular system. So we're starting to develop an understanding of the environments where you would not look for hydrogen, but we're still at an early stage of that. And we've also been looking at Brazil, again, sitting on top of a very old continental crustal system. We're working in the São Francisco Basin, a huge basin in Brazil. It's, again, an old continental rift. And in the sedimentary system, we do find exploration boreholes which are producing a mixture of helium, hydrogen, and methane. This is one of these halfway houses. The hydrogen has been degraded, but it's still present. And it's been degraded in the shallower systems which have been drilled, but we don't have a full understanding of what's causing that degradation, but it does raise the possibility that deeper within the system, we might expect to find a hydrogen resource. It's a little bit blurry, I'm afraid, but that earlier work from 2014 where we conducted a hydrogen survey, there's now a much more detailed review by Zegonic, where seeps and gas shows globally containing more than 10% by volume hydrogen. So that initial show that might indicate that it's worth looking at in more detail. We are seeing these globally: North America, Europe, Asia, Australia, South Africa, notably Africa and South America. China is not well covered, simply because I suspect it's not because the gas isn't there, it just hasn't been reported. But hydrogen seeps are widely found. I do want to make the point that most of my talk to this point has been focused on finding hydrogen within sedimentary systems. That's what we understand. This is where our understanding of how natural gas and oil and groundwater systems have accumulated. We understand the geological processes which allow and trap those fluids. But we've not looked for fluids in crystalline basement systems. Because why would you? Because our focus has been on finding oil and gas. But the crystalline basement, which represents the bulk of the continental crust, is highly complex. It represents geological processes from old sedimentary basins, meteorite strikes, volcanic systems, mountain belts, ophiolites, regions of that rock which is highly reactive, which have been pushed up onto the continental crust. Algal mats, old activity of life preserved on the surface, preserved in these rocks. We've not made an assessment of the potential of these different forms of crystalline basement to be fractured or to be exploited for hydrogen. So there's a lot of very interesting consideration to be done in that area. But I do want to leave you with a recent discovery in Mali, Burakabuga. This is a basin sitting on top of one of these ancient bits of continental crust, where hydrogen, and in this case, pretty pure hydrogen, up to between 80 to 90% of the gas which is coming out of a single borehole at volume is pure hydrogen. That hydrogen will have been generated by water-rock reactions. The detail on the amount of production that is coming out is limited, but it's clearly going to be of local significance, possibly of regional significance. But it does show you that there is hydrogen to be exploited. We're still at a very early stage of understanding where and how, but I think you can see that we're getting a good idea of the key considerations for developing an exploration strategy. So I'm going to leave you with some tick marks. We do have a good understanding of the rate of hydrogen generation. We've got a good understanding of what controls its release and the rate of release in those different types of environment, from volcanic to quiescent parts of the continental crust. We've got an understanding of the critical stage of gas phase formation, the types of geological structures that we would want to find in place to generate that strategy, with a big question mark over the continental crust complexity, where we just haven't looked yet. An open question still remains how long hydrogen survives in the near surface and how deep we may have to go to avoid microbial degradation of hydrogen resource. So work to be done, but I hope I've shown you that the potential gain in this area is huge. I suspect we will certainly find hydrogen resources of local significance, probably of regional significance, and almost certainly it will play a role in energy in a future sustainable energy mix. I don't think at this point we're going to replace the energy available, and we will still need hydrogen from green hydrogen, from blue hydrogen. So we will need all sorts of hydrogen for a green energy mix. But the prospects for natural hydrogen are looking good at this stage, and I will finish there. Thank you for your attention.
Thank you very much, Chris. I'd like to give you a small gift for thanking you for your presentation.
Thank you, Donald. That's very kind.
And also, I'd like to ask the audience if we have some questions on this absolutely fascinating talk. It's amazing to hear the work that you've been doing, Chris, and I suspect there are many parts of this region that we're in that would match the criteria that you've been talking about. So we have colleagues that are looking for black smokers in the Red Sea, so there is already evidence that they exist. We're trying to find them through some of the research that's going on. This is a very volcanic part of the world. There are many features, I think, that would be interesting for further exploration. So thank you for bringing us that information and telling us all about this exciting topic. So do we have some questions in the audience? Please, Hussein.
Hussein Khatib, KAUST, thank you very much for this fascinating talk. And it's great actually to hear that there is, besides the 3 colors of hydrogen, there could be maybe additional 4th color, which is a nice color, by the way. My question is actually 2 parts. One is related to the readiness or the maturity of the exploration and maybe the harvesting technologies right now for hydrogen, whether in from the basins or from the geothermal vents. And the second question is, this applies to all colors of hydrogen. As you mentioned, actually, hydrogen is very diffusive, right, molecule, and difficult to contain. So I wonder what's the, having a effective hydrogen, based economy, you need to transport hydrogen and store hydrogen and so on, which is also still difficult to do. So what's your thoughts about that? Thank you.
I'll address the last one first because it's the simplest. And one of the key technologies which we need to develop for a hydrogen economy, as you rightly said, is our ability to store it. And the diffusive nature of hydrogen makes that, it's not a challenge because we're starting to understand it. And so looking at geological systems where we can look at salt caverns, for example, as I showed there, natural anhydrite, which is similar in terms of its properties, is very resistant to gas diffusion. So there are prospects, for example, in big salt formations to either use existing cavities or generate cavities where we can store pressurized hydrogen and use those as local hydrogen supply. Not everywhere is going to have convenient salt or storage capacity, and technologies will need to be developed to store hydrogen at scale if we want to move to a hydrogen economy. So that remains a challenge. In terms of the development of the technology for exploring and exploiting hydrogen, it's at a very early stage. That example I showed in Mali was found by accident. That was a farmer drilling for water, and they hit a gas pressurized aquifer and found hydrogen, so which is surprised the farmer, I guess. There's a lot of interest in hydrogen as a component for helium exploration, because locally, if you're producing a helium and hydrogen-rich gas, that hydrogen can be used as a green energy source to power the compression systems, which allow you to liquefy the helium. So there's interest, and people are developing the economic models for hydrogen as a mixed gas. But the primary exploration and extraction of hydrogen has yet to be scaled up, and we're at an early stage. But I think some of the numbers I showed you in terms of volumes of hydrogen means that we only need to find a small amount of that potential for it to be a valuable commodity.
Yes, thank you so much, Dr. Chris, for being with us. So this is a very enlightening speech. I saw in one of your slides the Saudi Arabia peninsula here, and I saw the exposed kind of iron kind of crust on the west coast of Saudi Arabia. Do you suggest that there might be enough hydrogen and probably helium underneath those rocks? And if yes, how to discover them? And are they considered in the green hydrogen or the blue? Thank you.
Hydrogen, any hydrogen found would be gold because it would be natural. The key thing to understand would be the efficiency of gas release from beneath the sedimentary systems. So a study of the helium in the aquifer systems overlying the crystalline basement would be the first port of call to understand whether or not locally there is a flux which is preserved within the sedimentary stratigraphy. And calibrating that flux would then allow you to understand whether it could form a gas phase and how long that has been there, and whether that's a significant, has significant commercial potential. So there are techniques which are becoming available to us to understand that. And I'm talking to somebody in Saudi Aramco at the moment about a possible project to explore how we might use that to understand groundwater security, because the helium that comes up into the shallow surfaces can also be used to date groundwater. And if you understand the age of your groundwater, you can understand your groundwater resource. So the geological system, the geochemistry, it's an integrated system which gives us a lot of information about economic resource, energy resource, but also environmental systems at the near surface. So it's got a lot of potential to understand whether hydrogen is really locally significant, but the byproduct of that will be useful as well for environmental systems.
Mike.
Thank you for a very interesting talk. I was just wondering about the combustion products of hydrogen is water vapor and energy, correct?
Yeah.
But water vapor is a very powerful greenhouse gas. So I was just wondering, do you foresee any negative consequences of taking hydrogen that is buried underground and releasing it to the atmosphere as water vapor, and maybe that might have an impact on climate change?
My sense, and this is way beyond my field is that we've got a lot of water vapor naturally produced. Where you produce it will be the key component. So if you're producing water vapor in the upper atmosphere, then the droplets may be reflective, but we're doing that already with hydrocarbon combustion. My sense is that the production of water vapor isn't an issue. My sense is that there are other byproducts of burning hydrogen which we do need to be careful of, and those are the nitrogen oxides. So while you can burn hydrogen efficiently to generate just water and energy, if you're burning that in the presence of nitrogen, which is very, very likely, there are some studies which suggest that you can generate nitrogen oxides, which is not a healthy byproduct, and technology needs to be developed to make sure that's not occurring.
Please, Gaston.
Well, thank you, Chris. I'm assuming this accumulation of gas is sitting there in equilibrium, maybe quietly. Fast forward, exploration and extraction activities get started. That would probably impose some imbalance in that environmental system that is really over there. What would be certain precautions that we need to take care of early on so we wouldn't really impose some negative implications or consequences as we rush into exploring and extracting these gases accumulated over there?
No, I think that's a really important question. The environmental impact of any natural resource is something that we are becoming so much more aware of. The environments that we find hydrogen, helium, nitrogen, and methane at the moment are very deep. They're very deep and they're very saline. My sense is that their communication with the near surface is far removed, and that extraction of those gases will result in a small amount of re-equilibration at depth, but will be unlikely to have a big consequence at the near surface. So if you're extracting oil and gas at the near surface, then you've got to be very careful about the competency of your boreholes, whether as you extract oil and gas, you don't want that leaking into your drinking water aquifers. You don't want leakage of liquid hydrocarbons at the surface, and you don't want release of methane into the atmosphere. These are all bad things. Those are going to be minimal for a hydrogen, helium, methane. So, well, you need to watch out for the methane, but my sense is that extraction of a hydrogen, helium system, the environmental impact will be much, much lower than the extraction of methane from a shallower system.
Please.
You speak about methane as an indicator of gold and hydrogen. How about sulfur, which is also widely available, and also it's biologically active?
As an indicator of... Sorry, I didn't fully understand the question.
Sorry, gold hydrogen as well.
So you're asking about whether sulfur might be used as an indicator of gold hydrogen?
Well, hydrogen sulfide mainly.
Oh, I see. Yeah, that's a really good question, because the degradation of hydrogen through many forms is going to be a key component in removal of the molecular hydrogen. And microbial activity, we know from hydrocarbon systems, H2S is one of the byproducts of the microbial action. So it's not something I've thought about, and that's a really good point. So identifying hydrogen sulfide within your gas mix could be a line of evidence for hydrogen removal, primary hydrogen removal. Yeah, that's a very good point, well made.
Yeah, Yes, thank you for a very interesting talk. I have two questions. One is about the black smokers. There you have a concentrated source. Are there any estimates how much a single black smoker source is indicative of how much hydrogen is fluxing out at such locations?
Yes, but I don't have those numbers in my mind.
Yeah.
So the key components there is we've got an approximate rate of hydrogen generation from the entire mid-ocean ridge system. And I guess the key there is matching individual smokers which form small focus points on that.
Releasing a reservoir of...
That's right, and they're also ephemeral. They move and they come back, and they're active and they're not active. So I'm not sure that anybody has sat on top of a black smoker and fully calculated at that point the hydrogen generation rate.
But just to add to what Donald said, we also have lots of anhydrides and salt here in the Red Sea, so maybe this is a good place to look for. My second question is, I mean, given how difficult it is to find helium, do you really think that we are going to find enough natural hydrogen to move over to a commercial energy production? Just after all your studies that you have looked around the world? Well, so reactive. I mean, I know you get these high P-top numbers by accumulating over a very long time, 500 million years, but it's very reactive. Do you really think this is going to succeed?
I think when you look at those gases which are coming out of the crystalline basement, and we see that the hydrogen has not been reacted, and we've preserved the predicted hydrogen to helium ratios, telling us that there are environments in the crust where the hydrogen is not removed, that we've got that potential. We know in the deepest sediments, there are, as we start to explore for helium, and the helium exploration, we only started this 10 years ago, because there was no need for helium exploration because of the US Strategic Helium Reserve. It suppressed any need to look for helium. When that reserve finished, we started to look for helium, and we're finding it everywhere. You know, I'm involved in 6 startup companies, all of which have got really strong commercial prospects to take to market. Several of those have got hydrogen, significant hydrogen plays as part of that gas mix. So we are finding hydrogen as we look for helium. We've not looked for hydrogen as a primary gas at this point, but there are places in the geology where it is preserved, and from those numbers, you can see we only need to find a small part of that for it to be commercial. I do want to be cautious because we're at the various early stages, and the point you make about the preservation is the critical unknown component. But I will say that we've pretty much only looked in sedimentary systems. And if you want to find a system where your microbial activity and your potential for chemical reduction, chemical removal, you know, it's in the sedimentary systems. You wouldn't primarily go to a sedimentary system to look for hydrogen. But that is our first port of call because that's what we understand. It's the classic case of if somebody has lost their keys in the dark and they're found looking for the keys underneath the light and asked why they're looking underneath the light, it's because that's all they can see. And so I suspect we're in that stage at this moment.
Please.
Hi, I'm Ahmed Daoud, the Director of Innovation for the Royal Commission for Lord Ara. Thank you very much for a very enlightening talk. A couple of questions I had. One is, we see now with kind of the melting of ice across the planet that a lot of CO2 that's been trapped is being released. First question is, do we run the risk of exacerbating that or amplifying that effect when we're drilling and looking for hydrogen that's been trapped? And secondly, are parts of the planet that were submerged, whether recently, such as the Aral Sea, or even a long time ago, such as Al Ula, ideal candidates or good targets for exploring hydrogen that's trapped and seeing if that can be sequestered?
To answer your first question, the gain of a clean hydrogen energy source will put any energy costs and environmental damage, I think, into insignificance. We're currently extracting hydrocarbons, oil and gas, and we're looking at ways of converting that into a green energy form. If we can move straight to the hydrogen by the same process of extraction, then the environmental impact will be absolutely minimal. So the extraction of this source of energy, if it's viable, will have, I would say, negligible environmental impact. Whether or not we want to look at the local systems, the regional systems, in terms of the deposition of the right rock to trap hydrogen, it's also got to be lying on top of the right rock. So I would need to look at that convergence of those multiple parameters, and that's what we're developing at the moment. This high-level exploration strategy. Where in the world do those key components come together? And whether or not some of the locations you've mentioned have all of those parameters, I don't know at this stage, but would certainly be worth looking at.
My question was more that if you know that they have been submerged and these parts of the planet were part of the seabed at some point in history, whether recently, such as the Aral Sea, does that improve the probability, or does it not have an impact on the probability of finding hydrogen underneath them?
It's a part of the consideration, but when you look at the geological record, you will find that many of those geological layers in the past were formed beneath water. So as the geology of the sedimentary systems has changed and the continents have migrated around the planet, the local environment will have had seas form, seas disappear, mountain ranges form, mountain ranges erode. And so what you would be looking for is a significant event in that 100, 500 million year period, which has deposited that anhydrite, that evaporite. And I couldn't say whether the examples that you're quoting are significant in that context.
So can we just thank Chris one more time? Thank you very much, Chris.
Thank you. Thank you. Thanks very much.
Thank you.
Thank you very much.
Good morning and welcome to KAUST Research Open Week. My name is Nadia Karim.
And I'm Caroline Unk.
And thank you for joining us this morning. KAUST Research Open Week is the first time it's ever happened, and really what this week is about is celebrating the excellent science and research at KAUST. And the theme is Sustainability, Science for the Future, and the day's focus on our thrusts, so water, energy, environment, food and health, and the digital domain. Today focuses on water, and you'll join Caroline and I for the day to talk through various interviews with KAUST researchers. So please do stay tuned and enjoy the week. There will be lots of stuff in terms of presentations and demonstrations, and we'll walk you through them all. Caroline?
Yes, just before we go to the interviews, I just wanted to bring everyone's attention to our new research publication, KAUST Insight. You'll find it out around campus, and it's also available online at insight.kaust.edu.sa. In partnership with KAUST Insight, we have our ongoing publication, KAUST Discovery, and there's issue 12 of that available around on campus as well.
Thank you, Caroline. Stay tuned, guys, and watch out for the live interviews that are coming now. Thanks. Done. Sorry, I got so tongue-tied there.
I don't know which camera is I'm supposed to be looking at, clearly.
Okay, so Carolyn stays. I'll grab Atif for you.
Sure. Hi, and welcome back. I'm Carolyn Unk here, the Manager of Research Communication at KAUST. And for our first interview during Research Open Week, we welcome Atif Shamim, who is a professor of electrical and computer engineering. Welcome, Atif.
Thank you so much.
How are you doing today?
Awesome. It's nice booths out there and lots of technologies, so I'm enjoying the week.
Great. Thank you for being our first guest.
I didn't know I'm the first guest, but okay.
So tell us, Atif, tell us a little bit about your research, the scope that fits maybe into sustainability in line with our theme for the week.
Okay. Yeah, for sustainability, we are actually looking at from two angles. One is with respect to the environment, and the other is with respect to the renewable energy. So with the environment, you know, there's a lot of emphasis on this, especially talking about the Saudi Green Initiative. And the problem we see, or which we are trying to solve, is that a big area in the kingdom, actually in the world as well, but in kingdom particularly, is not monitored for air quality or environmental conditions. And the reason is that there's large area, and to put an infrastructure there with lots of sensors or weather stations is very, very expensive. So we look at this problem. If we can solve this problem if we can make like very low cost, dispersible, kind of disposable sensor nodes which have the wireless connectivity. And if these can be, let's say, spread out or dropped maybe through a drone or another way into large areas, and these can sense the environment, like the air quality, and then they can send this information through wireless connectivity to the servers or to the decision makers. So you are basically real-time monitoring that's what is missing. So any abnormalities or changes in that they can be reported, and of course corresponding actions can be taken. So as a first step, you need to monitor and find out the problem. So we are looking at that from protecting our environment, which is part of sustainability, through these wireless sensor nodes or wireless sensor network aspect.
Okay. What kind of challenges might you face with having these sensors everywhere, monitoring our environment?
That's a good question. Actually leads to my second part, which is the renewable energy. Now, if you are throwing or dispersing millions of sensors nodes for monitoring, and with changing their batteries or even charging their batteries or replacing their batteries is a nightmare. You cannot do it. It's almost impossible. So this means that you need to find a way where these either batteries could be charged or these sensors could be made self-powered through the ambient energy. So ambient energy harvesting. So that's another part of which is linked to sustainability, is that we are trying to create useful electricity, of course, for these wireless sensor nodes from the wireless signals which are all around us. So this is called radio frequency energy harvesting. And we are also trying to harvest energy with our partners in this project is MIT from USA, which is the day-night cycle. There's a temperature difference, and from that day-night cycle we can actually harvest energy. So from these two modes we can harvest enough energy to power these sensor nodes by themselves. And now question may arise, you know, there's solar energy all around, so how does these two technologies fit in? So there are many places where solar is not available. For example, in the night, in bad weathers, indoors, even so underground, you know, tunnels. So that's where these sources are very, very important, where solar is not available. And we have shown that we can actually harvest energy even if the sensors are embedded in the ground.
Wow.
So the challenge of powering these sensors is huge, but I think renewable energy is the answer to that.
Sounds great. Does your booth show any of this work, Atif?
Yes, actually the booth, which is the first one on the extreme end, shows these both these wireless sensor nodes, as well as it shows the energy harvesting modules, both RF and thermal energy. So everything is actually displayed there. So anybody or the visitors who are interested in this topic, they're more than welcome to come to our booth, and we will be able to show more and explain more to them.
You have some nice visuals there, I bet.
We do have, and you know, we will love to host people come to our booth, and we can talk more about this.
That sounds great. Thank you so much, Atif.
Thank you so much.
Thank you.
Thank you for having me here.
Thank you. Bye-bye.
Live.
Welcome back, everyone. I now have Hussein Hotite with us today. He's a professor of petroleum engineering. Welcome, Hussein.
Thank you, Caroline.
So, Hussein, when I think of petroleum engineering, sustainability isn't the first thing I think about.
Sure.
But I bet you've got some tricks up your sleeve. So please tell us how your research aligns with sustainability.
Sure. Well, thank you, Caroline. Yeah, as you mentioned, actually, I'm a professor in petroleum engineering. So our main focus is related to how would you produce oil, more oil, and more efficiently, and in an efficient way and a cost-effective way. But as you know now, there is the emerging challenge about the fossil fuels and its impact on the environment, greenhouse gas emissions, which is now a big challenge, right? And this is already recognized by essentially everybody that this is a problem now. At the same time, the fossil fuels remain a primary source of energy.
Mm-hmm.
And we all agree that renewable energy from solar, from wind, geothermal, and others are the energy of the future. So this is I think everybody agrees on that. But these technologies are not ready yet to displace or replace fossil fuels, all right? So all the calls right now to stop producing hydrocarbons, for example, and fossil fuels, it is not reasonable, in the sense that this technology, the alternative, is not ready yet, right? So we're gonna go through some transition period, right, until actually we get ready. And you've seen now many countries worldwide start to, announce, put their plans for emission, net zero emissions by 2050, 2060, and so on, right, for that. Now, until then, we need to find some solutions, right? Fossil fuels, especially oil and gas, will stay, a source of energy and primary source of energy till then. And this is where our roles comes in. What can you do within this transition period? Whether it is 30 years or 40 years or 50 years, you cannot keep emitting, right, these greenhouse gases to the atmosphere.
Mm-hmm.
So based on our experience as, from the petroleum engineering and this industry has a long experience in dealing with fluids, in dealing with gases, including carbon dioxide. And what we're working on right now, we try to switch or give a bit more attention to the environmental aspects, especially about CO2 emissions. So now, besides producing oil and gas, now we're trying to say, all right, what can you do about the emitted CO2? Can you capture this CO2 and do something about it? So this is where actually it comes. We have several projects we're working on right now. Some of them are related to reusing this CO2 for enhanced oil recovery, where you can entrap CO2 in the hydrocarbon reservoirs while actually producing oil. And then there's also other technologies related to capturing CO2, storing it, or injecting it into deep aquifers, and entrapping it permanently in underground.
Wow.
So, and of course, there's different challenges for these technologies that we are working on right now.
Okay. What's the greatest challenge, would you say?
Of course, this technology, it has two main components in it. One is, the capture part, right? So when you burn hydrocarbons, like gas, say, or oil, we use air, right? Air actually goes to the combustion engine, and with that, you emit basically nitrogen, for example, and other gases besides CO2. So when we store, the main actually challenge is mainly for CO2. CO2 is the if you like, the major component in these gases. So we need to separate it from the other gases, to capture it and eventually transport it to inject it in the subsurface.
Okay.
So one of the key challenges of this technology is how you reduce the cost of the capture right now. So the technology is there, we know how to capture CO2, separate it from the other gases, but there is actually cost component to it that is still preventing this technology to be extended at large scale. The other component to it is once you capture this CO2, now you need to compress it, drill deep wells, and inject it in what we call the reservoirs, which is underground formation that can entrap that CO2.
Okay.
So in the other component that once you inject that CO2, you need to make sure that you don't perturb this subsurface in terms of seismicity, for example. You don't damage the underground formation. You don't create, let's say, fractures or faults that eventually may allow that CO2 to leak and escape and get back to the atmosphere. So there is several engineering aspects that we need to study. We look at the rock mechanics, for example, the strength of the rock. We look at the CO2 interaction with rocks, like CO2 can change the acidity of water, for example, underground. It can dissolve some minerals, precipitate other minerals, and also interact with the subsurface fluids. It can dissolve in brine, for example, which is the saline water underground. So all these aspects need to be studied. And this here we have in our lab, actually at the Ali Nuaimi Petroleum Engineering Research Center. We look at these different mechanisms at different scale, starting from the molecular scale, looking at the micro scale, looking at how would that CO2 flow in the pore throats or the small spaces within the rock, how they flow within this rock, how they get entrapped within these pores, and also how they react with the rock. And then we take it to another scale. So we're going from the micro scale, we take it to a larger scale, which is a lab scale or core scale. We take rocks, we put them in the what we call core flood system, where we can mimic the subsurface conditions, like put it at high pressure, high temperature, inject CO2, see how that CO2 could displace the existing fluid, and then how it interact with it. Also, we look at the different mechanisms related to long-term mechanisms like reactivity, how would the reactions happen, and so on.
Okay. The monitoring, you do have to do quite a bit of monitoring of what's happening underground.
Right.
Is my memory correct in that you have a collaboration with Professor Satoshi Habuchi on this work? And actually we covered it in Insight. Right. So have you had a chance to see your story yet?
Yes, I did.
You had?
Thank you very much for it.
Is it what you expected? Was it what you hoped it would be?
Yeah,
tell the story behind the discovery?
And I think this is what's fascinating here about KAUST, right? Having all this expertise and the multidisciplinary, activities and work, because these problems are really major problems, right, that we're dealing with. Okay, and it is beyond the capability of one disciplinary or one institute or even one country. So it requires collaboration, right, from different aspects, different disciplinaries, and so on. And then that work that you mentioned with Professor Habuchi is although they are in the bioscience, right, technology, and we're in the petroleum engineering, so
seemed like such an unlikely coupling.
What's the coupling between these two? And for that work, because I mentioned that we are interested in understanding these fluids at the molecular scale, right? They are important for us because they are what determines, how these fluids behave, how they interact with the other surrounding formations, and so on. And working with Professor Habuchi helped us to try to look at that scale. And this is something was beyond our capability in the past. So we're able right now to tag some molecules and tag them, meaning that we put some fluorescent particles to them. And under the microscope, we're able to see at the dynamic conditions. So as these molecules flow, how they interact with the rock, for example. How would they get absorbed to the rock, get attached to the rock, and how they flow within the pore throats or the narrow channels within the rock. Sometimes they get tangled with each other, they accumulate, they can clog some pores. And this is something that we know from theoretical part that this is happening, right? So we have some analytical models that describe how these fluids flow, and interact. But this was the first time we're able to visualize them, look at that scale, and see, how this happens for it. So this was a great a great achievement in terms of actually trying to understand and helping understand how this mechanism happened.
It's so helpful to be able to actually visualize it with your own eyes. A model is helpful, but great to be able to visualize it.
Right.
It's such an interesting collaboration, so I hope everyone will check out the story in KAUST Insight. Professor Hotite, is there anything about your booth you'd like to tell us before we head off, or should we just tell people to pop over and have a look?
Absolutely. So we have very exciting booth here. There is three projects associated with it. And I need to mention about my collaborators on it. So one, we have Professor Carlos Santamarina, Professor Aboud Afifi, and also all the other faculty at AMPARG as well. So three projects on them. One is related to CO2 mineralization in volcanic rock. So we have some rock samples that actually shows how CO2 get mineralized naturally, actually turning CO2 into rock. Okay, and this is how the magic of chemistry happens. CO2 interact with like calcium cations, and they form calcite, rock. So we have some samples here. We also have some nice experiment. We talk about visualization, right? So, so we have a sand bank where we mimic the subsurface layering, so different formation, different layers, and we inject CO2 from. Like we mimic the injection well, we inject CO2, and we show you how CO2 actually get percolated and flow on the subsurface, and how it get entrapped in the reservoir. So we have the system here, and we have also the video that was taken for that experiment. So you can see how the CO2 flows in the subsurface.
Very
so
cool.
Feel free to stop by, and for everybody here in the community, stop by and have a look. I think it's very interesting to see.
Yeah, sounds great. I'm going to check it out.
Yes.
Thank you, Hussein.
Okay,
Thanks for joining us today, and have a good week. I'll see you at your booth.
Yes, see you. Thank you.
you. Hello, welcome back. I'm here now with Khalid Salama, Professor of Computer and Electrical Engineering. Welcome, Khalid.
Thank you so much for being here and inviting me to talk about our research.
Great to have you. So Khalid, we cover a lot of different areas of your research. Some of it appears in KAUST Discovery, soon to appear in KAUST Insight. Which area of the multi-dimensional research you do aligns with sustainability? Can you talk us through that?
So my research is on sensors, and you could find sensors around us everywhere, and many of these sensor applications actually have a vital role in sustainability. So for example, if you're looking about the environment is a key issue for us right now with the pollution that's everywhere. So having sensors around us actually helps us monitor the environment, monitor the levels of toxic gases, the hazardous materials, and then trying to mitigate their effect by maybe shutting down certain factories, directing traffic from certain areas, or even figuring out that there are some measures that has to be taken in order to improve the quality of air we breathe, the water we drink from the environment. So all of these are some of the applications of the sensors that we built. Other aspects of sensors in sustainability is food industry. Mm-hmm. We are interested in actually putting sensors in packaged goods so that we can actually detect if they're going to go bad early on, and also even in plant and precision agriculture. So figuring out when you actually water the plant, you don't have to water them all the time. When do you have to apply pesticides? When do you have to apply nutrients? So this is actually helps in sustainability.
Precision agriculture, that's a new kind of buzz term that's come
up. Yes, it's after the word precision medicine, or so this is the next thing, is precision agriculture.
So just not using the resources where they're most needed.
Exactly.
And also, if you're saying, for example, a plant doesn't need water and you're watering it, you may actually be some detriment to the plant. So
I mean, because it actually leads to a growth of certain funguses, and that could be harmful to the plant. So it's actually the best management of the resources you have. And in order to do management, you actually need to get real-time information, real-time data, and collecting this information through sensors. So we care a lot about building sensors that are actually collect data, transmit the data. So you need to actually transmit the data to the brain, and the brain is a place where it can actually collects all the data, makes correlations, detects patterns, and then makes decisions. So we also have interest in actually looking into computing systems that are sustainable. So you cannot be using all the time supercomputers that consume huge amount of power. So how can we actually process the data in a very efficient manner so that you can actually preserve the power?
Okay, is that what you would say is the greatest challenge?
So I would say that more and more people have worked on sensors, so that's pretty much stable. One of the biggest questions right now is analyzing the data. And it actually went into the extreme where we have data coming, but we don't have the processing power to process the data. So it's sitting there, no one is doing anything with it, no one is actually taking advantage of this data. So how to figure out how to take advantage of the data to make informed decisions is a key research area that many people worldwide are looking into, and definitely at KAUST we are doing a lot of that work. Power is also extremely important. You cannot actually build all the systems that consume huge amount of power. That's actually, this power comes from resources that might not be renewable. So that's also something that we really care about, how to do low power, or even much better is self-powered. So you use renewable energy, you don't actually have any batteries, you don't have any power sources, actually using sunlight or other sources of renewable energy to power your sensors or your systems.
Right, because I guess a lot of these sensors are in places where you can't really get access to them again to charge them or...
Yeah, so it's fun that you mentioned this. The cost of actually replacing the sensors or actually replacing the batteries is much more expensive than the sensor itself. So more and more the sensors are becoming cheaper, but then maintaining them is the most expensive part. So how to figure out that they can actually autonomous on their own, they can actually live for a long period of time and then power themselves, communicate. Sometimes you put sensors in places that you cannot really reach. So how to figure out how can you extract the data from them. So power wireless capability attached to the sensors is extremely important. Another thing is where can you deploy the sensors? Sometimes there is like a fire and you want to actually have those sensors on a drone zooming inside to check what's going on so that you can actually save lives. And this is another key issue, how to actually provide them with a long-term power to fly for a long period of time.
Okay. Sounds like you have your work cut out for you, Khaled.
We have lots of interesting problems. Lots of students are excited about this research area. It actually has many applications. It could be in the environment, could be actually for monitoring your health. I mean, more and more people are actually adopting a very healthy lifestyle, which is good, but then we need to keep continuously monitoring our body to figure out if we are losing some nutrients, if we are exercising. So we are working on lots of wearable sensors, so they can actually analyze your sweat real time and can give you information about your also some biomarkers in your body. This could be useful for early detection of certain types of diseases, so like cancers. That's one application. Some sensors actually could monitor your sleep, and that's extremely important. More and more we're living in a stressed environment and people are not getting the quality of sleep that they can get. So sensors find application everywhere. And that's actually good for us because we can actually find new and interesting applications. And it's not only for research, but it's actually a very applied area of research. So there are lots of real applications that people can benefit from.
Sounds great.
Thank you so much.
And you have a booth here
I have
Open
actually
Week, right?
2 booths.
You have 2. Okay,
yes,
can you tell us a little bit about
so
those?
So we have one booth on a gas sensor for detection of NOx. So this is one of the most dangerous compounds that actually come from combustion, so it comes from the exhaust from cars, from factories. And it actually exposure to a certain limit, very low concentration of nitrogen dioxide for 10 minutes can lead actually to a serious health problems. In fact, it can lead to death as well. So early detection of these gases, especially in environments where you have not only the real industries, but actually in mining industry, in oil extraction, how to have a real-time sensors that can detect very trace amounts of this gas and actually report it easily to people. It's actually good. So we build this transistor that actually can interact with the gas in the environment, and it's very specific to NOx, nitrogen dioxide, so that it can give us a signal right away and can get a siren, and it actually wirelessly connects to a central station to inform us about this exposure to the gas. And it's very small, very portable. You can actually walk around and carrying it. So if you are going into an environment you are worried about, it can detect, and you can actually put it in the different places, on walls, on lampposts and stuff like that. So that's the first booth.
That's very applied.
That's very applied. It's actually very applied. It's actually, one of our colleagues was passing by and said, like, this looks like a company product. When are you selling it? And we said, no, we actually like to build the full system. Something that really people can see not a lab environment, but take it to the next level, where we can translate our research to some prototype that companies can see what they are actually getting. The other booth is a completely different application, which is underwater communication.
Right.
So it's more and more we are interacting with the water. It's 97% of the Earth, and unfortunately, the technology is very primitive. And there are many situations now where actually importing lots of technology underwater. I mean, they are built here at KAUST. There was a technology invented a few years back. It's called iDive, where you can actually go with your iPad under the water and you can actually take videos and you can actually identify things. But the major problem is divers can only communicate with each other if they can see each other with hand signaling. So this is actually a big problem right now, because if you want to actually communicate, you have to see each other. So in murky environment, it's very tough. So we are actually developing a technology where divers can actually interact with each other. They can send messages using those iPads underwater, using acoustic signals, but at the same time, they can send videos and they can talk to each other. So in distress, if a diver is in distress, you need also to figure out his location. So how can you triangulate this location and actually send it to another diver, telling him, look, check on your colleague because there might be a problem. But even just, oh, I saw a nice fish here, come see it. So we are providing this technology of underwater communication. It's a very small device that's attached to your tank, and you can actually communicate with each other with videos real time with each other.
Very cool. As a diver myself, I can't count the number of times I've gone, wow, and then try to tell my friend, and it's gone.
So, we
that'd
are
be nice.
fond of telling people we are going to be Skyping underwater.
Skyping underwater.
Yes,
okay.
I mean, like you can do that. And it's not only diver to diver, it's diver to boat, boat to diver, diver to a station. So it's actually, think of it, we are building a complete network under the water where the divers are one component, but there are other components where we are working with other marine researchers at KAUST to put sensors on the coral reefs. So to monitor the temperature, to monitor the acidity, to monitor the salinity of the water, and that can give us early detection of warning signs. But then you need this information. So you need to figure out a communication mechanism so that you can send this data under the water to the base station so that you can actually send an alert signal and can do some action, early action. So preserve the coral reefs around us. And of course, the Red Sea is the ideal place for that. We have great coral reefs here and we don't want to lose them.
That's right. We sure don't. Yes. Thank you, Khalid. Thank you so much for joining us today, and I'll be sure to check out your book.
Thank you so much for being here.
Thank you.
Thank you. Bye.
So welcome back. I'm now joined by Manuel Aranda, Professor of Marine Science. Excuse me. Thank you for joining us, Manny.
Thank you for having me.
A lot of your work sits, I think, very closely with sustainability. Can you tell us a little bit about how your work pulls in sustainability?
So I'm working on corals and their abilities to acclimate and adapt to changing environments. And this is, of course, a very hot topic, given that climate change is having huge impacts on coral reef ecosystems. So we've been losing coral reefs at an unprecedented rate due to what is called coral bleaching. So heat stress events due to the increasing temperatures lead to the breakdown of the symbiotic relationship the corals have with their algae, which then leads to what we call bleaching. The colonies become pale white and basically slowly starve. And if the temperatures don't go down, then they basically die. And this happens on a massive scale. So we're basically using entire coral reefs throughout the world. And to put this in the context of sustainability, we're talking about an ecosystem that supports 25 to 30% of all marine animal species. So yes, small surface area, about 0.1% of the ocean floor is actually covered by coral reefs, but supporting almost 30% of all species. So you can envision what kind of impact it would have to lose these ecosystems for our oceans, right? So from a sustainability perspective, these ecosystems are essential for a healthy, functional ocean, and this comes with all the services this environment provides to us, from fisheries to just mere things like protecting our shorelines from erosion, which is very important to many of those small island states in the Pacific, if you think about it, but also other regions in the world, to ecotourism. So there's many countries where a lot of people rely on these ecosystems as their main source of income. From people who come, go diving, go fishing, and just enjoy these beautiful ecosystems.
Okay. This sounds very much like what you had written in KAUST Insight, our new research publication. You quoted, "The temperature is increasing so fast that corals might not be able to naturally adapt." So what should we do? If they can't naturally adapt, what options do we have?
Help them.
Okay.
Right? And that's where I came in. So originally I'm an evolutionary geneticist. And when you think about the current problem, corals have already endured much hotter temperatures, right? They actually were born 240 million years ago, right after the largest extinction event, you could say. But since then, they have survived the extinction event that killed the dinosaurs. They have survived the highest temperatures on Earth about 54 million years ago, the EMT. But during those times, they were basically facing temperature changes that took place over hundreds and even thousands of years. So as every other species, they could slowly adapt to these increasing temperatures. And sometimes when the temperatures went beyond what they could handle, you would see that coral reefs mostly disappeared and they survived in little patches. And once the temperatures got better, they basically bounced back and started building big reefs again. Now, looking at an ecosystem that provides essential services to us, we're now looking at the problem that the temperature increasing so fast that this natural way of adapting doesn't work. Very likely they will not go extinct. They might bounce back like they did before. But for us humans, it would mean that we lose a very important ecosystem that provides essential services. So they provide livelihoods to more than 500 million people. So what are they going to do if we lose them? So the way we think about it is that if the natural process of adaptation is too slow, the only way to move forward is to try to speed it up. And that's what we do with things like selective breeding, for example. We've recently shown in the publication that if we pick the right parents, we can produce offspring that already has about 3 degrees higher temperature resilience than if you use just the local parents that you find. So by selecting specific colonies and making sure that they can procreate faster and more broadly, we can maybe change the population structures and increase the number of colonies that will be more resilient. And to do this at a pace that allows us to maintain ecosystem functioning until, and this is a very important thing that needs to be stressed, we manage to curb emissions. Because like I said, there's a natural maximum level of temperature that they can withstand. If we do not stay below that, then anything we do won't be helping, right? So the only thing we can do with this is try to buy time. At the end of the day, we really need to curb our emissions to make sure that whatever we do will be fruitful also for the next generations.
Right. It's all connected, isn't it? And there's no one answer or one thing that must be done. It's a little bit of everything, which is, I guess, why it's a suitable topic for an open week about research, because just about everybody's research can contribute something. So that's really nice. And you have a booth here as well, right?
I have a booth.
What will I find if I stop by your booth?
So what you do there is, I mean, been talking about the research that we do, how we can speed up the process of adaptation, right? But this doesn't change that you still need to go out in the field and bring those individuals that you identified into the field in a way that allows them to actually procreate more efficiently and produce more babies. And for this, we have developed several products for what we call coral gardening and also coral nurseries. So the idea is current efforts are taking out corals from the environment, growing them in land-based nurseries or even in nurseries in the water, multiplying them and then bringing them back to the reef. Problem here is that you bring back exactly what you took out, right? So now we need a platform that allows us to implement all of these things that we research, so selective breeding, environmental hardening, so that we can bring out something that is more resilient than what we took out in the first place. And to do this at a much lower cost. The problem with corals is they need to go back into the water, which requires divers that then glue each fragment onto a suitable substrate, and this takes time and is quite expensive. So we're working on a platform that allows us to grow the corals already in a nursery in a way that allows us to track each individual and to learn about it. What is it that it likes? What are the environmental parameters that it prefers? Then we have a platform that allows us to bring in more fragments much faster. We're currently working on a Twitter challenge for one of our tiles that we use in the system that allows us to place about 50 fragments per diver per half an hour. This is about 5 times faster than any other method that is currently used in this field. So the idea is to have a complete platform where we can do the research, the selection of the right individuals in the nursery environment, understand where each fragment should go ideally in the reef so that we make sure it's happy and has the best chances of survival, and then being able to bring them out in larger numbers at larger scale to really tackle the problem at a level that, that is meaningful. To give you an idea, during the past decade, we have lost about 50% of the Great Barrier Reef. So it's a massive scale we're talking about. It's about the size of Italy. So imagine half of Italy and to be repopulated by actual corals, people planting them by hand. So this is a scale that is crazy to think about. So anything that we can do to speed up the process and to at least start restoring some parts so that these beta corals can now slowly take over the populations and spread out of the small area that we work on, is for us currently the best way forward to gain the scale that we require in the long run.
You mentioned 500 million people's livelihoods depend?
Yeah, likely more than that.
Will there be a stage where these people can take part in?
This is the idea, right? At the end, because we always talk about things like the Great Barrier Reef, but what about all these island countries in the Pacific? What about countries like Indonesia, the Philippines, where people are much, much poorer, where people really rely literally on coral reefs for the food on their table, literally, right? So the idea is to find ways how we can, for example, sell our products to rich people, like corporations that have large ecotourism projects, for example, and use that money to then fund restoration efforts in parts of the world where people cannot afford these things, but actually really rely on these ecosystems, right? So we're basically looking currently at different ways how to do that and to translate our science that we do to a broader, more meaningful scale.
Great. Well, that sounds good. I'll stay tuned for that and check out your booth later.
Thank you very much.
Thanks for joining us, Manuel.
Bye.
Bye-bye.
Through KAUST efforts for a more sustainable future. Come walk with me. Don't know how good. I'm going to take you through our booths here at KAUST. For KAUST Research Open Week, we have put out scientific demonstrations for you all to take a look at. Want you to walk through KAUST efforts for a more sustainable future. Come walk with me. Don't know how good that was. Hi, I'm Dr. Nadia Karim, and I'm going to take you through our booths here at KAUST. For KAUST Research Open Week, we have put out scientific demonstrations for you all to take a look at. Want you to walk through KAUST efforts for a more sustainable future. Come walk with me. Don't know how good that was. Hi, I'm Dr. Nadia Karim, and I'm going to take you through our booths here at KAUST. For KAUST Research Open Week, we have put out scientific demonstrations for you all to take a look at. Want you to walk through KAUST efforts for a more sustainable future. Come walk with me. I'm here at booth 23. It's about biosensing microneedle arrays designed from renewable polymers. I always love the word renewable because it just catches me, especially for the theme sustainability. Please introduce yourself and let us know a little bit more about this booth.
Hiya, I'm Dr. Huda Al-Fadus, a postdoc here in KAUST, and today we're showing an eco-friendly biosensing device that's 100% biodegradable. So the device is made of two parts. One is a polymer that is sourced from bacteria found in the Sahara here in Saudi Arabia and the sand.
Wow, so locally sourced.
It's locally sourced to reduce our healthcare footprint, carbon footprint. And it's also coated with a natural hydrogel called alginate. And alginate is also sourced from red algae found in the Red Sea. So it also can be sourced locally. So I can show you how they look like.
Yes, please. Tell us a little bit more about the microarrays. Why would we need them? Like, how are they used in healthcare?
Right, okay. So they would be little devices that are non-invasive. And those microneedles can go through the outer layers of the epidermis, and they can go to the superficial dermis and sample the interstitial fluid.
So it means it's going a little bit further than the skin, right? It's going deep down.
Yeah, no, just a little bit further than the skin, but not enough to penetrate into the blood vessels or like make you feel the pain through going to the pain sensor.
Excellent.
So it's just superficial. And the interstitial fluid carries biomarkers for various diseases in our body. So the microneedles are coated with this hydrogel because hydrogel carries the probes to detect these biomarkers. And so the probes will hybridize and bind to these biomarkers in our body, and then we'll be able to look at it again and see what's in there, basically, depending on what we're trying to detect.
Excellent, thank you. So take us through how then these are developed.
Okay, so there are two processes here. The first part is actually creating the microneedles. So I don't know if you can see them, but they are they're like square shaped. They're very small, and they're made, as I say, of a polymer. And then
Polymer is another word kind of for plastic. It's what plastics are made out of, or polymer. Tell us a little bit more about polymers.
Yeah, so the polymer that we have here, like I say, it's a natural polymer. So it's basically, it's like the material that you sort of make synthetic, hard devices.
So instead of using plastic, you're using naturally sourced, eco-friendly polymers.
That's it, yes. So it is 100% biodegradable, and it's completely natural and source. So it kind of allows us to be able also to reuse it. By the way, I didn't mention that, but also if you have this a particular device, you can remove the gel and reapply it again, so you can use it over and over again. But anyway, if you dispose it, it won't be bad for the environment because it can be degraded. So this is the mold that we make it from. Like I say, it's a very small mold, and
very hard to see that, but there was something in that file, yeah.
Yes. The polymer is PHB, so that's the name of it. You couldn't see it, you meant, but you can see it on the microscope.
I don't know if the camera can make it down into the microscope, but yeah, it's there. It's tiny. I guess that's why it's called microneedle.
Microneedle, that's it, yeah. Okay, he's probably able to catch it, I think.
So tell us a bit more about what's in this Petri dish here.
Okay, so this is the gel that I was talking about, the alginate hydrogel. And I colored it here with two different food coloring dyes, blue and red. And I want to show you how it's cross-linked. So it's usually liquid, and under room temperature condition, in aqueous solution, there is a salt here, that's calcium chloride. It can be cross-linked, so the calcium ions goes in between and make kind of an egg box structure, and it becomes solidified. So if I take some here, and the color can hopefully show you, and I drop even little drops in the liquid, you can see the beads forming.
That is so cool.
These are gel beads, yeah. So the whole idea is that these beads are put in this shape, and because they are in the salt, they will form basically independent solid structures like that. But also if we coat the microneedle with it, and then we apply the same solution, it will solidify on top of it. And so we have the coating layer, and then we functionalize it.
Excellent. Thank you, Huda. I'm very excited to see where your research goes. Thank you so much. Take care. Here at booth 13, we are looking at gas sensors. If you guys could introduce yourself and tell us a little bit about what's going on.
Hello, this is Maniteja. I'm a PhD student at Sensors Lab. I'm from Electronics and Computer Science Engineering Department.
Hi, I'm Alex Pribish. I'm a research technician and, yeah, same lab.
Alex, tell us a little bit about what's going on here.
Right, so we have this gas sensor that we have over here. Well, actually the sensing element is right over there, if you can take a view of that. And we made an integrated system for it so it can actually work in real time. So it's a nice little package that we made there. And it samples gas and warns the user using an alarm siren once it goes above 3 ppm, and then it does a very loud siren once it goes above 5 ppm.
Okay, so these gas sensors are really important, I guess, because there's a lot of pollution going on in the atmosphere at the moment. We're all aware of climate change. And in particular, this gas sensor can be used to detect pollutants. So can you just tell us a little bit about where we might put this gas sensor?
Okay, so I used to work in the mining industry, and over there they tend to use like ammonium nitrate-based explosives, and sometimes they don't properly detonate, and then you just see these huge clouds of nitrogen dioxide. So typically there would be a good way, and like open cast mining. Also underground there's a lot of diesel machinery, and a lot of sort of byproducts from diesel machines also have these like nitrogen oxides that are quite harmful to health, you know.
Excellent, thank you. Manny, can you give us a demonstration of what happens when it detects at a high level? Maybe put the sound on so everybody can hear.
So we have made sensors that are like transistor based. So what happens is these are very selective to the NO2 gas. So these transistor properties will change when there is NO2 gas at very low concentration. So if there is very high concentration, these transistors conductivity of these transistors decreases. And so we have made this detector such that if it goes to that level and it gives us siren.
Okay, are we going to hear the siren? Because I know it's like a fire alarm going off. Do we have sound?
We just muted it just because.
Put it on. Let's get everybody hearing it. So I think the one thing that is really important about gas sensors is they need to be very, very sensitive, right? It's very hard. It's in the atmosphere. It's not something that you can see. So when you say ppm, you're talking about parts per million. And the one great thing about this gas sensor that it is actually very highly sensitive.
Yes, these sensors are like very highly sensitive. It's like when compared to the reported sensors. And another interesting thing is most of the sensors that are already existing, they are very high power consumption because they will work at very high temperatures, but these work at room temperature, so they are low power consumption as well. And usually they will be selective to other gases also, but these sensors are very highly selective to particularly to NO2 gas. That's the another.
Love it. So it doesn't need a lot of energy. It's energy efficient. It's highly sensitive.
We could show you the siren now, but we don't want to really introduce any harmful gases in this environment here, you know.
Okay, that makes sense.
It's against OSHA regulation, if you know what I mean.
Okay, Brill, guys, thank you so much for your time today. Thank you. We're at booth number 22, AmbuBag-based emergency ventilator. I'm just going to get these guys to introduce themselves.
Hi, my name is Mohammad Popalzai. I work for prototyping and product development core labs.
Thank you, Mohammed.
And Dr. Ronan Carling, I'm working for the PCL lab as well in the core labs.
Brilliant, Dr. Ronan, thank you. So if you could tell us a little bit about your booth and what's going on here. Who wants to go first?
So, we are displaying emergency ventilator here. The concept came from when COVID-19 started, the pandemic started. The emergency ventilators were considered as a very important devices to cope with when the medical grade ventilators were not available. So the Olean Group and KAUST executives sat together and decided to design, develop and produce a ventilator for emergencies to cover for the Saudi Arabian shortage of ventilators, the medical grade ventilators. From KAUST, 3 departments worked together during the lockdown, the PCL, Prototyping and Product Development Core Lab, LEM, and CMOR. The engineers from all these 3 labs worked together and looked at the UK's healthcare and medicine regulatory standards and picked up the necessary or must-have protocols to build the emergency ventilator. the team from PCL, Prototyping and Product Development Core Lab, myself, Mishal Abdul Kareem, Michael Bearden, and from Engineering and Design, Dr. Ronan Carolan, and from LEM, we had Haris and Yusuf, and from Seymour, Andres, and Lloyd. They all helped to chip in and make this very difficult project working. So we can see on this booth that this is a live demo of the ventilator. It uses an ambu bag, which is self-inflating bag, which is used for transporting the patient in the ambulances. And the concept is to make it mechanically active. So we proved the concept, and fortunately there was no further need for these ventilators, and we didn't produce those. But we proved the concept, and this was a very successful project.
Amazing. Thank you, Mohammed. So maybe I can hand it over to Ronan now, because a lot of this was locally sourced, done in-house, and you can just tell us a little bit about the engineering.
Yeah, so as you can see here, the ambu bag, we purchased this online. Most of the valves came from CKD, a Japanese company, and the flow sensors. This is your simulation of a lung. This came from Switzerland. So basically what's happening is the ambu bag is being compressed. Here we can connect to medical grade oxygen. There's also an algorithm written to control the amount of oxygen that's required for the person's lung.
Wow.
Here on the actual program here, we can change the respiratory rate, we can change the tidal volume. So for a small person, you see a tidal volume of 250 milliliters. At the moment, we've it set to a ratio of 1:1. In a situation like this, with a 1:1 ratio, the person is really, really sick. So normally, you breathe at 1:2 or 1:3, but this is to deliver as much oxygen as possible, medical grade oxygen as possible. The larger the tidal volume, the more oxygen you can deliver, etc.
And the good thing about this is it depends, like the algorithm can work for a person, right? It varies for each person. Is that right?
For each person, the volume of their lungs, etc., etc. And again, you can't deliver a huge tidal volume for somebody with smaller lungs. Depending on how much oxygen is required, depending on how much they're struggling with the virus, it's how much oxygen you can deliver at one time. This is why the ratio will be 1:1. What else can I say? The pressures are set here. You see the tidal volume in, tidal volume out, all controlled by the algorithm.
Amazing. I think this is an excellent example of what the core labs can produce when they all come together from different strands of the core lab. So excellent work, guys. Well done.
Thank you. Thank you.
So I'm here at the semiconductor booth. This is a special booth that we've laid out during KAUST Research Open Week. We wanted to demonstrate KAUST efforts towards a semiconductor research, and I'm joined here by
Professor Xiaohang Li. I'm a faculty member of Electrical and Computer Engineering and Applied Physics. So I'm one of the organizers of this semiconductor booth. And at KAUST, there are over 20 faculty working either directly or indirectly on semiconductor. And as you know, semiconductor is probably one of the most important foundation of modern society. Wherever you use electricity today, you have semiconductor chips at the core of the product. So here at KAUST, we have organized a semiconductor booth and trying to selectively covering some of the highlights of our semiconductor research. So here we have, faculty members such as Professor Nazek working on ultra-flexible and ultra-stretchable silicon solar cells, and this can be used in many, many scenarios from human to different machineries and to different vehicles. And here we have Professor Thomas Antopoulos, and he has many excellent works on next generation oxide, high speed and low power diodes and transistors for different applications from smartphone to electric vehicles to communication. And right here we have Professor Atif Shamin's work on the fully printed, ultra low cost and also flexible switches and reconfigurable filters. This can have many applications in 5G, 6G and communication and beyond. And here, this is the research of my group. And so we have recently developed the world's first fourth generation CMOS. And that is after the first, second, and third generation CMOS invented by different companies such as Bell Lab, Boeing, and General Motors. And we are very proud of this work, and we hope this work can lead to a revolution in the digital technology in the future. And right here we have Professor Shahika Inan's work. She is a leading expert on the organic electronics, and particularly sensors and different devices used for monitor human health and also environment. And right here, again, we have Professor Thomas Antopoulos' work on his advanced devices for different applications. Yeah.
Thank you, Jahong. This is fantastic, and I think it's worth saying that as well. The semiconductor research, it's a multi-billion-dollar research area, right? So what KAUST is doing is we are creating and developing the next generation of semiconductors.
Correct.
Excellent. Thank you so much for your time.
Thank you very much.
15. We're going to talk about CubeSat remote observation platform. So if you guys just want to introduce yourself first, then we can go from there.
Samer Masharawi. I'm the field research engineer of the HALO group, Hydrology and Land Observation group, with Professor Matthew McKibben.
Hi, my name is Oliver Lopez. I'm a research specialist in the Hydrology, Land and Observation group.
Hi, I'm Marcel. I'm postdoc in the HALO group also.
Okay, so tell us a little bit about what's going on here. Samar, I'm going to get you to just walk aside because we've got this really funky looking prototype here. Tell us a little bit more about what's going on.
So this is one of the new trend satellites that was created over the past maybe 10 years. This is one model that is one-to-one scale of how the actual satellites are. As you can see, it's a, what do you call it, a shoe box size satellites. I mean, the main advantage of them, they are much cheaper than the larger satellites. They are launching several of them. I think now there is more than maybe 100, 200 of them. We, as a group, we designed our own specification of one of these satellites that we are going to launch, I think, sometime next year. Our satellite is specifically designed for our application. As I can show you here, we have what we call it multispectral cameras. This one has 6 lenses, which means 6 bands. Each of these bands can give us information about the vegetation, either water consumption, health, chlorophyll content, what do you call it, NDVI, one of the parameters that can tell us how healthy the plant is. This is another example, and this has 5 bands. Our satellite will have 100 bands. And the whole point of this research is to test which band can give a better explanation or better information about the vegetation, health, water consumption, etc.
Okay, so I was just about to ask, what does it actually do? But you just said it there at the end, so that's pretty cool. I guess in a world where there's water scarcity and we need to, be very careful with how we use our water, and especially when we all want to feed the world by 2050, right? This satellite is going to do that job. Can you just tell us a little bit more about the application? Who wants to take that?
Sure. So at the moment, we're using traditional large-scale satellites launched by NASA, by the European Space Agency, but these are multi-billion-dollar projects. So using this satellite data, it can help us to monitor over a large-scale area, even the whole Saudi Arabia. We can monitor where are the agricultural farms. So our group identified more than 30,000 center pivot fields in Saudi Arabia, which was a huge task. And now we're also including water use models. And yeah, this satellite, as Samer mentioned, has even more information that we can use to further use these models.
Excellent. It sounds like you guys are doing an amazing job, especially for the future of Saudi Arabia in the world. Thank you so much.
Thank you. Thank you.
Booth 50. I'm here at booth 21. I see COVID in the title, which is very relevant for the world we live in today. Can you introduce yourself and tell us a little bit more about this booth?
Yeah, my name is Muhammad Tehseen. I'm a research scientist working under supervision of Professor Samir Hamdan in KAUST. We here developed this R3T one-step RTQ PCR kit.
Okay, so a kit is very important, right? Because first of all, we can make COVID tests, but we need all the reagents to make a COVID test. And this is when you say you've developed a kit, you have developed all the reagents that might go into a COVID test. Is that right?
Yes, exactly. Since last year, when pandemic struck the world, there was a huge demand of testing the COVID-19 in the world. So all the companies were rushing in to produce these kits, and ultimately, due to the huge demand, there was a less supply, and we have to buy the kits at very high prices. So we came up with this idea, and under the umbrella of KAUST R3T team, we started producing this one-step kit. Since we had the expertise of protein biochemistry and enzymology for the last, we are working in around more than 10 years in this area. So we took this responsibility and successfully produced this kit, which is as sensitive as the other kits in the market. And currently we are producing around more than 3 million reactions a week. And if we have a small facility for the production, we can just increase this to around 10 million a week. And one of the KAUST startup is currently using this kit, and it is successfully deployed here. And they are taking samples from the KAUST and the surrounding areas as well. And I think they already took more than 10,000 tests with our kit.
Amazing. What's the name of it?
R3T. One-step qRT-PCR kit.
Excellent. And it's funny because everyone was locked down, people were at home, but you were in the lab working really, really hard.
Yes, exactly. We have to come, but thanks to everyone for the procurement, all the university teams who supported for the materials to provide us. And luckily, we have all the ingredients in our lab. And then we successfully did it within no time. I think it took us 3 to 4 months to do that. Yeah.
That's an excellent point. I guess when everything closed down, so did the borders. And so what you have developed has all been in-house, locally sourced. So that's an excellent point. You know, it's very important when borders close and you can't get, right? There's the supply chain closes as well. So congratulations on this.
Thank you so much. And plus one most important thing about this kit is this is RT and the PCR. So it means it's not just restricted to COVID-19 testing. So it can be used for testing of any pathogens, any virus, RNA or DNA in humans, in animals, and in the plants. But since it's a pandemic, so everyone is about COVID, so we are using it for the COVID testing at the moment.
No, very well done.
And also, the cost of the kit is around 3 cents per reaction, which is around 100 times less what is available in the market. And at the same time, the sensitivity of the kit is as sensitive whatever available in the market for us.
This kit has definitely been used on me multiple times, so thank you. It was very low cost.
Thank you so much.
It was excellent. The future of healthcare right here. Thank you so much, Mohammed.
Thank you so much, Nadia. Thank you.
You ready? Okay. You ready? Okay. I'm here at the semiconductor booth. This is a special booth that we've laid out during KAUST Research Open Week. We wanted to demonstrate KAUST's efforts towards a semiconductor research, and I'm joined here by
Professor Xiaohang Li. I'm a faculty member of Electrical and Computer Engineering and Applied Physics. So I'm one of the organizers of this semiconductor booth. And at KAUST, there are over 20 faculty working either directly or indirectly on semiconductor. And as you know, semiconductor is probably one of the most important foundation of modern society. Wherever you use electricity today, you have semiconductor chips at the core of the product. So here at KAUST, we have organized a semiconductor booth and trying to selectively covering some of the highlights of our semiconductor research. So here we have, faculty members such as Professor Nazek working on ultra-flexible and ultra-stretchable silicon solar cells, and this can be used in many, many scenarios from human to different machineries and to different vehicles. And here we have Professor Thomas Anthopoulos, and he has many excellent works on next generation oxide, high speed and low power diodes and transistors for different applications from smartphone to electric vehicles to communication. And right here we have Professor Atif Shamin's work on the fully printed, ultra low cost and also flexible switches and reconfigurable filters. This can have many applications in 5G, 6G and communication and beyond. And here, this is the research of my group. And so we have recently developed the world's first fourth generation CMOS. And that is after the first, second, and third generation CMOS invented by different companies such as Bell Lab, Boeing, and General Motors. And we are very proud of this work, and we hope this work can lead to a revolution in the digital technology in the future. And right here we have Professor Shahika Inan's work. She is a leading expert on the organic electronics, and particularly sensors and different devices used for monitor human health and also environment. And right here, again, we have Professor Thomas Anthopoulos' work on his advanced devices for different applications. Yeah.
Thank you, Jahong. This is fantastic, and I think it's worth saying that as well. The semiconductor research, it's a multi-billion-dollar research area, right? So what KAUST is doing is we are creating and developing the next generation of semiconductors.
Correct.
Excellent. Thank you so much for your time.
Thank you very much. Yeah.
So I'm
My name is Donald Bradley and I'm the Vice President for Research at KAUST. KAUST Insight is a new publication. It tells the story behind the discoveries that come out of our research. We're interested to show the social side of science, how new ideas in science sometimes come from chance encounters. We want KAUST Insight to be a publication that helps people to understand where our science is going. That is influenced by many factors, by the needs of Saudi Arabia, by the Vision 2030, also by our own strategies, the things that we think are important for KAUST to be part of and to be working on. Some key directions include work that is being done to address climate change, and in particular the work that we're doing within the circular carbon economy. We have a circular carbon initiative that is focused on finding ways to reduce the amount of carbon dioxide that is produced, to remove it, to recycle it and to reuse it. Another key component of our science going forward is to work on the Red Sea. The Red Sea is a very exciting opportunity for research. It's critical to the future of the kingdom in terms of the development that's taking place through the Giga projects. And it's a fascinating environment in which many different areas of science come together. Another critical area is how society is changing. The gender balance in science, and we want to be part of that journey. We want to show how diversity is important to taking science forward. We want to show how women in science are contributing and how they are taking leadership in driving forward many of the ideas that we have for development in KAUST. You will find that all of these topics are featured within KAUST Insight, and we will be looking to develop these stories as the publication goes forward over time. There are many new areas that are coming forward in science in terms of the digital transformation, in terms of the energy transformation. There are lots of different directions in which our science will be progressing, and we look very much forward to being able to expose those areas to our readership of KAUST Insight.
Come on down, loads of space. Everyone is a bit sluggish after lunch. So it's my pleasure to welcome you all back after lunch, and I would like to introduce Dr. Najat Ashri, our Vice President for Strategic National Advancement.
السلام عليكم جميعاً ومساء الخير وأهلاً بكم في أسبوع الحيوي مليء بالبرامج المثيرة. أنا بس أخذت جولة سريعة برا وأعتقد أنه من الأسابيع المناسبة لتواجدكم معنا فيه، وإن شاء الله يعود بالنفع علينا وعليكم جميعاً بعونه تعالى. Good afternoon, everyone. It's a great honor for me to be introducing today's keynote speaker at the first day of KAUST Research Open Week, Dr. Adil Bushnak, Chief Executive of Bushnak Group. No matter what I say about Dr. Adil, it will not really reflect his very exciting and fulfilling journey in terms of serving research in specific areas, and of serving education as well as the youth of this nation. Adil Bushnak is not a conventional businessman. He was one of the first to have realized the importance of dealing with the challenges facing Saudi Arabia. He has some very clear ideas about desalination, water conservation, as well as education, which I hope he will share with us today. The Bushnak Group, which he owns with his brother Faisal, is Saudi Arabia's best-known private water company and one of the pioneering forces in the kingdom's water business. The group's core activity is desalination and has more than 30 years' experience in the business. However, this is just a part of Dr. Bushnak's busy portfolio. He was involved in setting up the Arab Water Council, of which he is a co-founder, and which is structured along the lines of the World Water Council. He is also launching a trust fund for water desalination in some of Saudi Arabia's remote villages. On top of these impressive contributions, Dr. Bushnak played a pivotal role in founding the Jeddah Water and Power Forum when he served for 8 years as the director of Jeddah Chamber of Commerce and Industry. What one quickly realizes, talking to Dr. Bushnak, however, is that his real passion is in education. After a stellar academic career, gaining a bachelor's degree and a Master of Science from the University of California at Berkeley, Dr. Bushnak earned his PhD in civil engineering from the University of Michigan. After that, he returned to the kingdom to serve in King Saud University in the early 70s as a faculty member. In spite of joining and starting up the first Saudi water treatment company, Al-Kawthar Industries, academia has remained close to his heart ever since. In fact, I had the honor of being on a founding board of one of Saudi Arabia's universities with him, and has been deeply, deeply impressed with his commitment and dedication to the advancement of higher education in the kingdom. There is no doubt that Dr. Bushnak's career thus far demonstrates how to strike a balance between academic study, business, public sector, and philanthropy. It demonstrates how to achieve success on all levels while making the world a greener, more sustainable place. Dr. Bushnak continues to invest time and resources to provide balanced solutions for the water, food, energy nexus. So without further ado, it gives me great pleasure to invite Dr. Bushnak to begin his presentation detailing how the best future technologies will support in making Saudi Arabia, as well as other regions of the world, green and sustainable, while incurring minimum cost, both financial and otherwise. Please help me welcome Dr. Bushnak. Thank you.
Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillahir Rahmanir Rahim. I'm proud of this great introduction and happy to be with you. I think this is the place to innovate and to be prepared for the future. I will speak in English, although I like to speak in Arabic, but to be just the language that can be understood by all. And of course, my presentation will start with how to encourage students and young entrepreneurs and innovators to continue and to do more. And then I will talk about 3 innovations that most recently I have been working on, well, since one of it since the 90s, so it is not recent. But let me start with the how, yes, I will move to this, how to be a future leader, because I hope many of you students of KAUST will be future leaders of innovation and change and for the better. And as I said, from my experience since the 80s about new technologies and promoting it and building not just ideas like I'm talking about today, but also manufacturing. The first Saudi manufacturing company to manufacture reverse osmosis back in the 80s, I was honored to welcome King Khalid to open it. But it took SWEC 30 years to agree that seawater reverse osmosis is much better than what they have been used to for more than 70, 80, 100 years. Anyway, my advice from my experience, I try to summarize what the process I went through, and make you that you want to please your creator, not please X or Y or Mr. or your boss, or please Allah, because He will help you. Because without that, it's not possible to achieve what you want. And very important task, all of us, we have to teach ourselves what is new knowledge, useful knowledge, not just repeated knowledge. And this is why I am interested in education, to prepare future leaders, because innovators and future leaders will not learn just unusual in a classroom. So you have to teach yourself every day. Even if you are 70s or reached 80s, it is your duty to teach yourself. And seek new future options. And this is a very important item, because really many people do not agree with you, because if your idea or technology is something out of the box, they want the familiar solutions. And even experts and professors, they don't want to listen, they don't want to learn something new, and they want to promote what they are familiar with. So this is important, that you select something new, creative, especially integrated. So sustainability, I'm happy to talk about sustainability, because sustainability cannot be achieved unless it serves all parties, environment, business, government, NGOs, and so on. I'll move starting and behaving NGO, yes, because from my experience, I started the first International Desalination Association. Well, I co-founded it, but I was not the first president. The first president was American, because this was registered in America. But I became the first Arab or non-American president of the International Desalination Association back in the 70s. And after that, I started or co-started many branches of whatever, call it Arab League or even Gulf League. Now I'm happy they are still continuing to hold conferences. And of course, I'm still helping them if they need my help, but I'm happy that I'm not responsible anymore about everything I co-started. And think outside this social, familiar, present boxes also, to connect societies and parties, government, NGOs, business is not easy, because every organization, official, or even business, they think of certain solutions or ways to achieve their goals. And be prepared to expected, unexpected. Yes, this is important also, to not think that you will succeed from day one. There will always be obstacles and problems, and continue, persist, and expand your business in other countries. Yes, very important that you find local partners or operator or manager. I started maybe in more than 5 countries, joint partnership, and was advisor to international water companies. But anyway, so this is a summary of basically it is your responsibility to think and to act to be a future leader. I'm happy KAUST exists, and we are here to see that how we can together start the future. This is the advantage of KAUST. It brings many ideas and sciences and technologies together, because the future solutions will not be from single science or area or technology. It has to include, incorporate, integrate all possible to increase benefits to as many people as people. I don't think about benefits to me, to myself. As long as NGOs are benefiting, I am happy. And also how to serve as many people as possible with this new technology, and serve environment, sustainability. All these are important factors. So I will move to what I just introduced myself now. What is طيبة Knowledge Waqf? Education to improve, NGO to develop education, because really our education system still needs a lot of changes and improvements. I'm happy we're starting, but we are far away from what we could do. Teach yourself at home. You don't have to go to school. Of course, attend a lecture from home. You don't have to go to a lecture to learn. And start your own organization to discuss and brainstorm in order to innovate. So we go now to future innovation, sustainable technologies which need additional investment. Really, I am talking about these 3 because it is not yet well developed, or the benefits are not well known, although you will see benefits of some, like seawater farming. But I want to start with SkyTab, which is what I am working on for helping the innovator more than 7 years ago. And many friends and relatives and partnership advised me not to continue, but I am continuing. And I hope this year with KAUST, I hope KAUST will be the technology partner, because I want the technology to to locate it, to be Saudized, in order that Saudi Arabia can benefit more with new inventions, innovations, and exporting the product. So I will start with that and then talk about my experience in the 90s with building the largest seawater irrigated farm and using saline water for cooling, which was tested and built the first unit here in KAUST. The SkyTab process really can change the world, not just Saudi Arabia, but of course Saudi will benefit more, and countries, Arab countries like Egypt, because it can produce rainwater, amount you want, where you want, for the purpose you want. All this, artificial rain does not solve this problem. The success of artificial rain today, around 20%, less or more, but it is close to 20%. While this technology, yes, we will start with 50% success rate, but I think in 10 years we will achieve 80% because of the knowledge, especially if we know about the weather and how to measure all these variables which will affect the rain and forming a cloud. But I believe, because this is what you start the process of forming a cloud in a blue sky. Today there is no blue sky, there is no cloud. And you can form a cloud, but a cloud will not rain, it will dissipate unless you condense it to make it rain. So this is the change in the, because these are, we are using natural process where negative ions go and combine with positive ions. Everywhere the sun produces positive ions, and then if you send negative ions, they will combine and form H2O. And provide not just fresh water, but many issues. You know, I hope Aramco will benefit as well by mineral extraction and hydroelectric power the country, because it is hydropower is much less costly today than solar or wind or other renewable today present renewable energy. And of course, because the process has to start, of course, better, easier, cheaper, with less equipment. You can, as you are close to the sea, where the source of humidity in the air. And then you have to have more units to follow that cloud to be able to condense it and make it rain where you want. And the drones solve the problem, because it was 7 years ago, there were not many drones. So the inventor used a four-wheel drive. I told him this is impossible to follow a cloud without a road. So just have a four-wheel drive will not help you to follow the cloud. So, but drones now, you can follow the cloud cheaper than helicopters and airplanes as artificial rain they use. And this is, you can see, area close to the coast will be much easier to make it green and produce water at few percentage cost of desalination, seawater desalination. So this is something that will change the future, because Saudi Arabia is the largest country in the world that needs desalination, and we cannot continue building more and more desalination plants, and the effect and impact on environment or cost. The other benefits of SkyTab technology, other than it's providing sustainable water and food sources, because over farms there is humidity, so even if your farm is away from the sea, still the chances of making it rain or recycling the water in the ground will be easier, and helping our country how to make it green, because it is much simpler and easier and less costly how to make our country green. Providing hydropower, because again we have many mountains and valleys, and it is not costly to build a high dam in Saudi Arabia, because the higher the dam, the more energy you can produce and export. So I hope in the future we will export hydropower, not more than maybe oil. And also very important is reducing summer temperature, because you need the cloud, even if you don't want rain, just to reduce the heat of the sun during summer days. And this can make a difference in our cities, in our Makkah, Medina, where Hajj during summer is very difficult. So if you can have a cloud over Makkah region all day, it will not be difficult to make Hajj during summer. And even air temperature, because if you can convince every ship, there are thousands of ships going around the world every day in the sea. If just one equipment, one unit can produce a cloud in the sky, imagine the thousands of clouds will reduce the temperature of the earth. I'm sure there are other benefits that from other specialities. These are so far what we can count, but I'm sure in the future will be more benefits as we discover what are. And this is what I tried for years in the 90s, and I could not convince 4 ministers of agriculture to use this company. Safola was the biggest partner. There were 40 partners, Saudi partners in the company. And to produce this saliconia plant, which the Europeans eat it as a salad. Our camels, Saudi camels, love to eat it, and as well as we tested it with other animals, they all find it, of course, they eat more or less, depending on how much water they have and they can drink. And this is the intake of the farm. The farm, 50 hectare in Ras Al Khair now is an industrial zone on the Gulf. But you can see we are using even irrigation by machine. And of course, we did many research with the help of King Saud University and other Saudi universities, King Faisal University. And you can see how the green area all. And we discovered how to use natural items, not chemicals. All these were natural treatment to protect, again, to protect the plant from this is the last innovation that I'm happy that KAUST was interested, and we built the first, how to use seawater to cool greenhouses, because greenhouses needs cooling in order, and of course you need water. So the advantage here, you can produce sweet water or pure water, as well as cooling from seawater sources. So we have 2,000 kilometers on the sea in Saudi Arabia that can be can produce a lot without causing any using our water sources. طيب, my wish today is just to open more questions. How I can help you, an inventor. I am very happy today. I visited the exhibition and met many inventors. And just my request, all those who want to invest, to allocate at least 10% of their profit or share to NGO. If not طيبة المعرفة, the NGO you select. But I am keen that business and government and society, we work together because the NGO is a future. And this is the last slide. So I finished here and will be happy to answer any questions or make appointments to meet with people who want to ask me questions, because especially if you want to buy a share in SkyTab technology, 2020-21 is the best time for you to buy share, because next year when you innovate, it will be less percentage. And as more people get involved, of course, the cost of buying 1% or 10% will be much more. So I hope KAUST will benefit as NGO, and because that will make the technology more useful, more important, and more international. How to, and I hope future Saudis, graduates of KAUST will go to other countries in order to initiate, start, and operate these drone-driven units, because all you need are just batteries inside the box to produce the negative ions. So you don't need complicated equipment, and I hope there will be a Saudi manufacturer. If you know any Saudi manufacturer interested to produce ions and negative ions and drones, because all this will be exported, and how to integrate our effort. And I will stop here and say, thank you very much.
Thank you very much, Dr. Adil, for your interesting talk. I think, Dr. Adil, maybe you want to remain here for a few minutes, just in case there are any questions.
Sure.
So if you have any questions, there are microphones in the middle there. So please, go ahead.
Good afternoon. This is Omar Oda from MIWA and the UNDP. First of all, it's an honor to listen to your very interesting presentation. And it's an honor again to meet you, Dr. Adil. Since I moved to Saudi Arabia 10 years ago and started my business in water and being a professor in the water, you are one of the persons that I have enjoyed learning your publication and enjoyed discussing before your work and your achievement. I have a quick question for you. I know that you are working in different developing countries with supporting NGOs there toward achieving sustainable development goal and providing water and sanitation service to the poor rural area. My question to you, what else can be done? How developed world, how rich country like the GCC can support the underdeveloped country to achieve the SDG targets, especially for water and sanitation, SDG 6? That's the key question, which is I want to hear your vision on this. Thank you very much.
I hope. Hello, you hear me?
I think you can use this one.
Yes, maybe better. Of course, we have to start the company to be able to support poor countries and local or international NGOs to produce water where it is needed, especially for people before animals and before plants. And my priority now is to start the company, Saudi company, which will export the technology worldwide. Okay, and then there are so many NGOs, international and local, who will be happy to support others. But this is next, because we have to start the company, and it has to recover its investment or pay back its profit and so on in order. And this is why I'm insisting and requesting every investor to assign percentage of his profit or share to NGO. So then the company will help NGOs. And of course, in the future, with this Saudi holding company, we will start localized companies in Egypt, in Jordan, and I want to serve Arab countries because they need this technology, as well as many African countries who are poor and arid. So I think if, as I said, if KAUST is involved, and I hope NEOM will be, we will test, make it rain in NEOM, unless KAUST wants to make it rain here. They, of course, they have to pay for the equipment needed to make rain. But NEOM and Aramco may be easier, more interested to do it there. And then it will be international solution. Anyway, I'll be happy to help anybody who wants to. There are already so many. Water.org is the latest I discovered, international NGO that provides water or help to poor people to obtain water. So there are already, every day you discover people who can connect with you or complement you and so on.
I think there is another question over there. Any other questions? Doctor, تفضل.
Thank you very much for this excellent presentation. I have two questions. The first one is about, and thank you for sharing these words of wisdom, and that you started with. We know that actually there's no successes without failures. So I wonder, from your experience, what are the lessons learned for future leaders and inventors, right? How to learn from their mistakes and failures, if you like, to build for their future. So this is the first question. The second question is about water usage here and the water supply. And we know that actually here in the kingdom, part of the water, of the fresh water comes from underground water, which is, we know that this is not sustainable. Unfortunately, this water is not renewable. So what's your thoughts about that, and if the sky tap technology can help to maybe reduce the usage or exploration of the fresh water or underground water in the kingdom? Thank you.
Yes, to your first question, you have to be persistent and not give up in order to succeed. Think of positively, in the sense, yes, I will not repeat what I did last few years. I will start new. And Allah will help you. You don't know how this relationship or information and support will come, as long as you continue. And even if the first, like the seawater farming, I don't, it is success in every technical item, lacking, not succeeded to convince the agriculture minister to approve. Always said, we used 4 years, we planted that, and the salinity of the earth under the farm did not increase. Why? Because we flushed, because we are close to seawater, so we were flushing seawater. But the people in the agriculture, oh no, you will make our earth saline, more saline, so not allowed. Now, the other question on, remind me, groundwater, yes. This is, you're right, this technology, SkyTap, will save the groundwater and natural sources of water for sweet water because we don't use all humidity in the air exists everywhere, every time, many thousands, I don't remember the figure, how much the crowd or the humidity in the air compared to seawater and so on. It's a huge quantity. And so we are using sustainable sources because every day, the sun and the wind increase what comes out of the sea, the humidity. So all we have, and as I said, discovered today how to measure amount of humidity or this or that in the weather, so that will make you study better. What does it cost for me to make it rain? Should I make it rain today or this week or next month? All this depend on information about the weather and the environment. And this is where technology need to combine in order to be easy. So this is why I hope KAUST will be involved or actively involved in order not just to learn from the innovator how to start, but how to proceed, how to exceed, how to expand. And I hope I answered your question.
Thank you very much, Dr. Adil. Help me please in thanking Dr. Adil for this wonderful thoughts. Thank you.
Welcome back, everybody, to our interviews, our live interviews here in Building 19 in KAUST. I'm joined by a special guest today. They are not from KAUST. Thomas, could you please introduce yourself?
My name is Thomas Hoover. I used to actually work at KAUST years ago.
That's right.
I spent 3.5 years here working at Coastal Marine Research Lab. But before that, I was working at Mbari. I worked in the Navy. I worked in a company that did stealth technologies on naval warships. A varied career over 3 decades before I found myself here.
Excellent. Why are you here during KAUST Research Open Week? It's something to do with MATE, am I right?
MATE. MATE is Marine Advanced Technology Education. So the short and simple of this is 20-some years ago, the industries that work in the ocean figured out that they were struggling to recruit new people to work in those fields. So they reached out and they created a nonprofit that's tasked with teaching STEM to students and engaging them into the ocean careers. That's what MATE is about. I'm here to bring that program to Saudi Arabia via KAUST.
Amazing. So you're inspiring and engaging with the younger generation.
Yes.
Brilliant.
Yes. You get a gray hair, you start thinking about life beyond that.
What do you think MATE will bring to the Kingdom of Saudi Arabia?
Well, what I've seen so far, last week I held a professional workshop development to develop people here who will reach out to local schools and create ROV clubs that then go into a MATE competition. Those people are Saudi nationals who have engineering degrees. Half the group I was training is female, half is male.
Amazing.
We're reaching out to all these schools, grabbing these kids at about age 12, bring them into the program, get them started on this ROV competition, and then every year the competition changes a little bit. Every year the level they can compete at increases potentially.
Wow.
Over the time frame, initially it's with fairly small level, easy to do things that a 12-year-old can handle.
Brilliant.
But it goes all the way up to sophomore, junior level of college, and we have MIT schools and of that caliber competing in this competition. That outreach, that growth of STEM is what we will bring.
Excellent. So it's an international competition. There's a different challenge each year.
Yes.
And you're here in the Kingdom of Saudi Arabia to inspire and engage with young researchers that will hopefully be part of a regional competition for MATE.
Exactly correct.
Okay, amazing. Thank you, Thomas, for joining us today.
Thank you for having me.
Thank you to our listeners as well. They have to shut down our microphones. Okay, welcome back. I am joined by Professor Susanna Nunes, and she's going to talk to us about her research today. Susanna, your exact title at the moment, because you have just been given the title of Vice Provost, is that right?
Yes.
So introduce yourself, please.
So I'm Susanna Nunes, I'm Vice Provost at KAUST, and I'm also a polymer chemist. So I've been working with sustainable materials, materials for sustainable energy for very long before joining KAUST. And my work, my lab works with sustainable separations. So we develop membranes that will enable separations with less energy that is done nowadays.
Brilliant. So very relevant to the theme of KAUST Research Open Week, which is sustainability, science for the future. So when we talk about separation, I think maybe for our viewers, they might not know exactly what it is, but separation, so chemical separations or separations of fluids, perhaps maybe in desalination or gases and whatnot, it is very energy intensive.
Yeah.
And so you develop membranes that perhaps are low cost, better quality and less energy intensive, so therefore they're more sustainable. Can you just tell us a little bit more about your research?
Yes, exactly. I think you summarized very well. I think our goal is to develop new materials that will enable different separations. For instance, for gas, for natural gas. So things that we have a series of processes in this transition that we are now to a more sustainable future. We have huge opportunities for membranes to facilitate, have less energy in separating, for instance, natural gas or methane from nitrogen or other kinds of gas separation, vapor in air conditioning, dehumidification. We are working on the cooling initiative at KAUST. But separations could be simple ion separation in a more sustainable desalination that is not only drinking water but harvesting valuable ions. I think there's many companies interested in that now. And it could be what I think is very important is to have a chemical industry which is more, that is really integrated, in all processes integrated, so that we can substitute a lot of the thermal separation process that costs a lot of energy. I read that 15% of the world energy consumption is in separations. So if we can substitute, it's a really very important goal.
Absolutely, and especially for the Kingdom of Saudi Arabia, as you mentioned, air conditioning. So the Kingdom of Saudi Arabia is very hot. We use a lot of air conditioning here, and I'm sure that it's very energy intensive for us. And also your work relates very closely to the circular carbon economy, and in Saudi Arabia we have the Circular Carbon Economy National Programme, and here in KAUST we have the Circular Carbon Initiative, and also the Saudi Green Initiative, which has just come up recently. It's very relevant to that as well, where we're going to plant billions of trees with water, where it comes from, who knows, and also reduce our energy consumption as a nation as well. So thank you, Susanna. Thank you for the research that you do here at KAUST.
Thank you very
Brilliant.
much.
KAUST. For KAUST Research Open Week, we have put out scientific demonstrations for you all to take a look at. Want you to walk through KAUST's efforts for a more sustainable future. Come walk with me. Here at booth number 1, which looks like a very interesting booth, very relevant for where we are in KAUST. We're on the coast of the Red Sea. So please introduce yourself and tell us a little bit about this booth.
Yes, my name is José Hilton, and here I'm presenting an innovative system for divers. If you love diving, this is the booth for you. So basically, we have created an underwater communication system that will allow the divers to communicate underwater. Here, they can use their own smartphones that will be translated. You create a wireless network inside of the water that would be translated in acoustic signals, and these signals will travel inside of the ocean, and you allow them to communicate the same way that you use smartphones outside the water, you use inside of the water.
Which isn't easy, right? Because of the water, you've got waves, you've got murky waters.
Not only that, for example, all the RF communication that we use, that we have for granted here in the system right now, like in the open air, does not work in the ocean because...
So RF is radio frequency?
Yes, RF is radio frequency, and this is all absorbed inside of the water. So you need this kind of technology to translate the RF to something that can conduct in the water, that is acoustics.
Excellent, well done. This is fantastic. Who knew that we would be communicating underwater? Thank you very much, Jose.
Welcome.
I'm here at booth 23. It's about biosensing microneedle arrays designed from renewable polymers. I always love the word renewable because it just catches me, especially for the theme sustainability. Please introduce yourself and let us know a little bit more about this booth.
Hi, I'm Dr. Huda Al-Fadus, a postdoc here in KAUST, and today we're showing an eco-friendly biosensing device that's 100% biodegradable. So the device is made of 2 parts. One is a polymer that is sourced from bacteria found in the Sahara here in Saudi Arabia and the sand.
Wow, so locally sourced.
It's locally sourced. We reduce our healthcare footprint, carbon footprint. And it's also coated with a natural hydrogel called alginate. And alginate is also sourced from red algae found in the Red Sea. So it also can be sourced locally. So I can show you how they look like?
Yes, please. Tell us a little bit more about the microarrays. Why would we need them? Like, how are they used in healthcare?
Right, okay. So they would be little devices that are non-invasive. And those microneedles can go through the outer layers of the epidermis, and they can go to the superficial dermis and sample the interstitial fluid.
So it means it's going a little bit further than the skin, right? It's going deep down.
Yeah, no, just a little bit further than the skin, but not enough to penetrate into the blood vessels or like make you feel the pain through going to the pain sensor.
Excellent.
So it's just superficial. And the interstitial fluid carries biomarkers for various diseases in our body. So the microneedles are coated with this hydrogel because hydrogel carries the probes to detect these biomarkers. And so the probes will hybridize and bind to these biomarkers in our body, and then we'll be able to look at it again and see what's in there, basically, depending on what we're trying to detect.
Excellent, thank you. So take us through how then these are developed.
Okay, so there are 2 processes here. The first part is actually creating the microneedles. So I don't know if you can see them, but they are they're like square shaped. They're very small, and they're made, as I say, of a polymer. And then
polymer is another word, kind of for plastic. It's what plastics are made out of, or polymer. Tell us a little bit more about polymers.
Yeah, so the polymer that we have here, like I say, it's a natural polymer. So it's basically, it's like the material that you sort of make synthetic, hard devices.
So instead of using plastic, you're using naturally sourced, eco-friendly polymers.
That's it. Yes. So it is 100% biodegradable, and it's completely natural and local source. So it kind of allows us to be able also to reuse this. By the way, I didn't mention that, but also if you have this a particular device, you can remove the gel and reapply it again, so you can use it over and over again. But anyway, if you dispose it, it won't be bad for the environment because it can be degraded. So this is the mold that we make it from. Like I say, it's a very small mold, and
very hard to see that, but there was something in that file. Yeah.
Yes. The polymer is PHB, so that's the name of it. And Oh, you couldn't see it, you meant, but you can see it on the microscope.
I don't know if the camera can make it down into the microscope, but yeah, it's there. It's tiny. I guess that's why it's called microneedle.
Microneedle, that's it, yeah. Okay, he's probably able to catch it, I think.
So tell us a bit more about what's in this Petri dish here.
Okay, so this is the gel that I was talking about, the alginate hydrogel. And I colored it here with two different food coloring dyes, blue and red. And I want to show you how it's cross-linked. So it's usually liquid, and in the room temperature condition, in aqueous solution, there is a salt here, that's calcium chloride. It can be cross-linked, so the calcium ions go in between and make kind of an egg box structure, and it becomes solidified. So if I take some here, and the color can hopefully show you, and I drop even little drops in the liquid, you can see the beads forming.
That is so cool.
These are gel beads, yeah. So the whole idea is that these beads are put in this shape, and because they are in the salt, they will form basically independent solid structures like that. But also if we coat the microneedle with it, and then we apply the same solution, it will solidify on top of it. And so we have the coating layer, and then we functionalize it.
Excellent. Thank you, Huda. I'm very excited to see where your research goes. Thank you so much. Take care. Here at booth 13, we are looking at gas sensors. If you guys could introduce yourself and tell us a little bit about what's going on.
Hello, this is Maniteja. I'm a PhD student at Sensors Lab. I'm from Electronics and Computer Science Engineering Department.
Hi, I'm Alex Privish. I'm a research technician and, yeah, same lab.
Alex, tell us a little bit about what's going on here.
Right, so we have this gas sensor that we have over here. Well, actually the sensing element is right over there, if you can take a view of that. And we made an integrated system for it so it can actually work in real time. So it's a nice little package that we made there. And it samples gas and warns the user using an alarm siren once it goes above 3 ppm, and then it does a very loud siren once it goes above 5 ppm.
Okay, so these gas sensors are really important, I guess, because there's a lot of pollution going on in the atmosphere at the moment. We're all aware of climate change. And in particular, this gas sensor can be used to detect pollutants. So can you just tell us a little bit about where we might put this gas sensor?
Okay, so I used to work in the mining industry, and over there they tend to use like ammonium nitrate-based explosives, and sometimes they don't properly detonate, and then you just see these huge clouds of nitrogen dioxide. So typically there would be a good way, and like open cast mining. Also underground there's a lot of diesel machinery, and a lot of sort of byproducts from diesel machines also have these like nitrogen oxides that are quite harmful to the health, you know.
Excellent, thank you. Manny, can you give us a demonstration of what happens when it detects at a high level? Maybe put the sound on so everybody can hear.
So we have made sensors that are like transistor based. So what happens is these are very selective to NO2 gas. So these transistor properties will change when there is NO2 gas at very low concentration. So if there is very high concentration, these transistors conductivity of these transistors decreases. And so we have made this detector such that if it goes to that level, and it gives us siren.
Okay, are we going to hear the siren? Because I know it's like a fire alarm going off. Do we have sound?
We just muted it just because.
Put it on. Let's get everybody hearing it. So I think the one thing that is really important about gas sensors is they need to be very, very sensitive, right? It's very hard. It's in the atmosphere. It's not something that you can see. So when you say ppm, you're talking about parts per million. And the one great thing about this gas sensor that it is actually very highly sensitive.
Yes, these sensors are like very highly sensitive. It's like when compared to the reported sensors. And another interesting thing is most of the sensors that are already existing, they are very high power consumption because they will work at very high temperatures. But these work at room temperature, so they are low power consumption as well. And usually they will be selective to other gases also. But these sensors are very highly selective to particularly to NO2 gas. That's the another.
Love it. So it doesn't need a lot of energy. It's energy efficient. It's highly sensitive.
We could show you the siren now, but we don't want to really introduce any harmful gases in this environment here, you know.
Okay, that makes sense.
It's against OSHA regulation, if you know what I mean.
Okay, Brill, guys, thank you so much for your time today. Booth number 22, AmbuBag-based emergency ventilator. I'm just going to get these guys to introduce themselves.
Hi, my name is Mohammad Popalzai. I work for prototyping and product development core labs.
Thank you, Mohammed.
And Dr. Ronan Carling, I'm working for the PCL lab as well in the core labs.
Brilliant, Dr. Ronan, thank you. So if you could tell us a little bit about your booth and what's going on here. Who wants to go first?
So, yeah, we are displaying emergency ventilator here. The concept came from when COVID-19 started, the pandemic started. The emergency ventilators were considered as a very important devices to cope with when the medical grade ventilators were not available. So the Olean Group and KAUST executives sat together and decided to design, develop and produce a ventilator for emergencies to cover for the Saudi Arabian shortage of ventilators, the medical grade ventilators. From KAUST, 3 departments worked together during the lockdown, the PCL, Prototyping and Product Development Core Lab, LEM and Seymour. The engineers from all these 3 labs worked together and looked at the UK's healthcare and medicine regulatory standards and picked up the necessary or must-have protocols to build the emergency ventilator. The team from PCL, Prototyping and Product Development Core Lab, myself, Mishal Abdul Kareem, Michael Bearden, and from Engineering and Design, Dr. Ronan Carolan, and from LEM, we had Haris and Yusuf, and from Seymour, Andres and Lloyd. They all helped to chip in and make this very difficult project working. So we can see on this booth that this is a live demo of the ventilator. It uses an AmbuBag, which is self-inflating bag, which is used for transporting the patient in the ambulances. And the concept is to make it mechanically active. So we proved the concept, and fortunately there was no further need for these ventilators, and we didn't produce those. But we proved the concept, and this was a very successful project.
Amazing, thank you, Mohammed. So maybe I can hand it over to Ronan now, because a lot of this was locally sourced, done in-house, and you can just tell us a little bit about the engineering.
Yeah, so as you can see here, the AmbuBag, we purchased this online. Most of the valves came from CKD, a Japanese company, and the flow sensors. This is your simulation of a lung. This came from Switzerland. So basically what's happening is the AmbuBag is being compressed. Here we can connect to medical grade oxygen. There's also an algorithm written to control the amount of oxygen that's required for the person's lung.
Wow.
Here on the actual program here, we can change the respiratory rate, we can change the tidal volume. So for a small person, you see a tidal volume of 250 milliliters. At the moment, we've it set to a ratio of 1:1. In a situation like this, with a 1:1 ratio, the person is really, really sick. So normally, you breathe at 1:2 or 1:3, but this is to deliver as much oxygen as possible, medical grade oxygen as possible. The larger the tidal volume, the more oxygen you can deliver, etc.
And the good thing about this is it depends, like the algorithm can work for a person, right? It varies for each person. Is that right?
Each person, the volume of their lungs, etc., etc. And again, you can't deliver a huge tidal volume for somebody with smaller lungs. Depending on how much oxygen is required, depending on how much they're struggling with the virus, it's how much oxygen you can deliver at one time. This is why the ratio will be 1:1. What else can I say? The pressures are set here. You see the tidal volume in, tidal volume out, all controlled by the algorithm.
Amazing. I think this is an excellent example of what the core labs can produce when they all come together from different strands of the core lab. So excellent work, guys. Well done.
Thank you. Thank you.
Hi, you're
I'm a
at
faculty
booth.
member of electrical and computer engineering and applied physics. So I'm one of the organizers of this semiconductor booth. And at KAUST, there are over 20 faculty working either directly or indirectly on semiconductor. And as you know, semiconductor is probably one of the most important foundation of modern society. Wherever you use electricity today, you have semiconductor chips at the core of the product. So here at KAUST, we have organized a semiconductor booth and trying to selectively covering some of the highlights of our semiconductor research. So here we have, faculty members such as Professor Nazek working on ultra-flexible and ultra-stretchable silicon solar cells, and this can be used in many, many scenarios from human to different machineries and to different vehicles. And here we have Professor Thomas Anthopoulos, and he has many excellent works on next generation oxide, high speed and low power diodes and transistors for different applications from smartphone to electric vehicles to communication. And right here we have Professor Atif Shamin's work on the fully printed, ultra low cost and also flexible switches and reconfigurable filters. This can have many applications in 5G, 6G and communication and beyond. And here, this is the research of my group. And so we have recently developed the world's first fourth generation CMOS. And that is after the first, second, and third generation CMOS invented by different companies such as Bell Lab, Boeing, and General Motors. And we are very proud of this work, and we hope this work can lead to a revolution in the digital technology in the future. And right here we have Professor Shahika Inan's work. She is a leading expert on the organic electronics, and particularly sensors and different devices used for monitor human health and also environment. And right here, again, we have Professor Thomas Anthopoulos' work on his advanced devices for different applications. Yeah.
Thank you, Jahong. This is fantastic, and I think it's worth saying that as well. The semiconductor research, it's a multi-billion-dollar research area, right? So what KAUST is doing is we are creating and developing the next generation of semiconductors.
Correct.
Excellent. Thank you so much for your
Thank
time.
you very much. Yeah.
So I'm here at the semiconductor booth. This is a special booth that we've laid out during KAUST Research Open Week. We wanted to demonstrate KAUST's efforts towards a semiconductor research, and I'm joined here by
Professor Xiaohang Li. I'm a faculty member of electrical and computer engineering and applied physics. So I'm one of the organizers of this semiconductor booth. And at KAUST, there are over 20 faculty working either directly or indirectly on semiconductor. And as you know, semiconductor is probably one of the most important foundation of modern society. Wherever you use electricity today, you have semiconductor chips at the core of the product. So here at KAUST, we have organized a semiconductor booth and trying to selectively covering some of the highlights of our semiconductor research. So here we have, faculty members such as Professor Nazek working on ultra-flexible and ultra-stretchable silicon solar cells, and this can be used in many, many scenarios from human to different machineries and to different vehicles. And here we have Professor Thomas Anthopoulos, and he has many excellent works on next generation oxide, high speed and low power diodes and transistors for different applications from smartphone to electric vehicles to communication. And right here we have Professor Atif Shamin's work on the fully printed, ultra low cost and also flexible switches and reconfigurable filters. This can have many applications in 5G, 6G and communication and beyond. And here, this is the research of my group. And so we have recently developed the world's first fourth generation CMOS. And that is after the first, second, and third generation CMOS invented by different companies such as Bell Lab, Boeing, and General Motors. And we are very proud of this work, and we hope this work can lead to a revolution in the digital technology in the future. And right here we have Professor Shahika Inan's work. She is a leading expert on the organic electronics, and particularly sensors and different devices used for monitor human health and also environment. And right here, again, we have Professor Thomas Anthopoulos' work on his advanced devices for different applications. Yeah.
Thank you, Jahong. This is fantastic, and I think it's worth saying that as well. The semiconductor research, it's a multi-billion-dollar research area, right? So what KAUST is doing is we are creating and developing the next generation of semiconductors.
Correct.
Excellent. Thank you so much for your time.
Thank you very much. Yeah.
Remote observation platform. So if you guys just want to introduce yourself first, then we can go from there.
Samer Masharawi. I'm the field research engineer of the HALO group, Hydrology and Land Observation group, with Professor Matthew McKibben.
Hi, my name is Oliver Lopez. I'm a research specialist in the Hydrology, Land and Observation group.
Hi, I'm Marcel. I'm postdoc in the HALO group also.
Okay, so tell us a little bit about what's going on here. Samer, I'm going to get you to just walk aside because we've got this really funky looking prototype here. Tell us a little bit more about what's going on.
So this is one of the new trend satellites that was created over the past maybe 10 years. This is one model that is one-to-one scale of how the actual satellites are. As you can see, it's a, what do you call it, a shoe box size satellite. I mean, the main advantage of them, they are much cheaper than the larger satellites. They are launching several of them. I think now there is more than maybe 100, 200 of them. We, as a group, we designed our own specification of one of these satellites that we are going to launch, I think, sometime next year. Our satellite is specifically designed for our application. As I can show you here, we have what we call it multispectral cameras. This one has 6 lenses, which means 6 bands. Each of these bands can give us information about the vegetation, either water consumption, health, chlorophyll content, what do you call it, NDVI, one of the parameters that can tell us how healthy the plant is. This is another example, and this has 5 bands. Our satellite will have 100 bands. And the whole point of this research is to test which band can give a better explanation or better information about the vegetation, health, water consumption, etc.
Okay, so I was just about to ask, what does it actually do? But you just said it there at the end, so that's pretty cool. I guess in a world where there's water scarcity and we need to, be very careful with how we use our water, and especially when we all want to feed the world by 2050, right? This satellite is going to do that job. Can you just tell us a little bit more about the application? Who wants to take that?
Sure. So at the moment, we're using traditional large-scale satellites launched by NASA, by the European Space Agency, but these are multi-billion-dollar projects. So using this satellite data, it can help us to monitor over a large-scale area, even the whole Saudi Arabia. We can monitor where are the agricultural farms. So our group identified more than 30,000 center pivot fields in Saudi Arabia, which was a huge task. And now we're also including water use models. And yeah, this satellite, as Samer mentioned, has even more information that we can use to further use these models.
Excellent. It sounds like you guys are doing an amazing job, especially for the future of Saudi Arabia in the world. Thank you so much.
Thank you.
Thank you.
Welcome back to our viewers watching live. I'm joined here by the head of KAUST Smart, Mohammed. Please introduce yourself.
Well, good afternoon, everybody. I'm Mohammed Abdul Al. I'm the Director of Digital Experience and Innovation. I'm looking here. I'm the Director of Digital Experience and Innovation, also known as KAUST Smart, and I'm glad to be here at the KAUST Research Open Week.
Amazing. Mohammed, thank you so much for allowing KAUST Smart to be a part of KAUST Research Open Week, because it is an amazing thing going on at KAUST. Can you tell us a little bit more about KAUST Smart? What does it do, or what does it intend to do? How are we going to make KAUST smarter?
Well, KAUST Smart in a simple terms is the arm that allows us to experiment and do more interesting ideas at the campus of KAUST. We want to try things out. We go and look into what's coming in next in the future and give it a shot at KAUST. We like to use the city of KAUST and the community of KAUST as the way to engage in examining and testing how these concepts fit, not from a technology side only, but also from a human-centric perspective. So obviously it relies a lot on the KAUST research and the outcomes and ideas that the KAUST faculty are doing.
Amazing. And not only does it kind of talk about smart technology, because we were the first in the kingdom to have the autonomous vehicle.
Correct.
Thanks to you. And you know, it's not only just about making, let's say, technology smarter, but also the way we live. Maybe if you could talk about a little bit about smarter offices, smarter homes, because it's not even something tangible sometimes that you can see, right? It's making them more energy efficient and...
Correct. Smart does not mean digital. Smart means how do you make people's life better and easier? So we look at it from a human perspective around experiences. We talk about mobility experience, living experience, dining and eating experience, and even a visitor to come into KAUST experience. And underneath all of that comes a set of technologies, but also more importantly, a set of design principles of how can we make that journey better and easier for the people. So this is what underpins KAUST Smart. It's not about technology only, it's really about human experience coupled with technology and experimentations.
Amazing. And you also have your KAUST Central app.
We have the KAUST Central app. The app is a platform that connects all these experiences together. So when we talk about mobility, dining, visiting, we believe that an app, one maybe big one, maybe a few small ones, but an app platform is one way to connect the dots. It's not the only way, because a lot of things are sometimes physical, you know, how you navigate and find your way around the campus, signage. But an app definitely is one way that connects all these things together. So KAUST Central is the university app to download and basically start to navigate your way around KAUST.
Great. And if anyone's physically here, they know that we have a lot of the QR codes around to download KAUST Central app.
Correct.
But you can find it in the App Store. And you can find KAUST Smart here in Building 20, Level 3, if you want to come
Building 20,
visit.
Level 3, we have a small booth set up just to kind of answer questions and engage anybody who's interested in more, because we welcome ideas and we welcome crazy thoughts. So if you have something interesting you want to try, we're the group to try with.
You look like a guy who has some crazy thoughts, all right. And there's tours to the KAUST Smart House
And there's a smart house, obviously, that our friends at Facilities Management has constructed. And it's again, it's a living experience of what does a smart house of the future should look like. It's not about tech, it's also about energy, water, and sustainability of a home.
Excellent. Thank you, Mohammed, for
You're
joining
welcome.
us today.
Glad to have you.
Thank you.
Thank you very much.
Hi everyone, we're back, and here with me now is Kyle Larson. He's a professor in bioengineering. Welcome, Kyle.
Thanks very much. It's great to be back. We were just discussing it's been about a year since our last meeting on camera, so it's very fun to be here.
Right here in this very same spot
Exactly
about the
same
Circular
spot.
Carbon Initiative.
Same blazer, everything.
Excellent. Well, it's good to have you back again.
Thanks.
Thank you. Can you tell us a little bit about your research, how it aligns with sustainability, the theme of our Research Open Week?
Sure. It's kind of funny to discuss sustainability because it's actually at the core of what we do. So we, in our group, work with microalgae and microalgal engineering. So algae are lovely green things or sometimes red things or other colored things like you see in these flasks here. And they can be found all over the world. So they're found in the ocean, in the Red Sea, obviously, but also in soil and on the land. And even if you wipe the side of a building, sometimes you can get algae that's been growing there. So this is why you see green things around water sources. If you have a little bit of trickle of water somewhere, often green things grow, and that's because algae are very prolific organisms. So the reason that we say that sustainability is at the crux of everything we do is that algae are photosynthetic organisms. So they use light for energy, just like this bright light here that's shining on us or the sun outside. And they take that energy and they use it to grow on carbon dioxide. So carbon dioxide is, of course, a greenhouse gas that we're giving off in unsustainable quantities right now in our linear economy. And the idea is that algae use that carbon source as their main carbon source for growth, just like plants do. So we all know that plants breathe in CO2 and breathe out oxygen. Algae do the same thing. So we work with algae, especially microalgae, because they're very easy to scale up, because they double forever as long as you give them the right conditions to grow. And you can see examples of that here. So this is a saltwater alga, something from the Red Sea. And this is a freshwater alga, which actually was found in a potato field in Idaho. And so we are able to use what we call synthetic biology now, which is the ability to code DNA in a computer and then synthesize it as a chemical in its sequence and put it into the algae, work with their native genome and its regulation, and convert that carbon dioxide into products that we're interested in. So algae itself is a very valuable biomass. It produces proteins, oils, sugars, all kinds of things that we can use just like we would get from plants. But because we can engineer them, we can also produce things like medicines or perfume products or different colors of pigments. So they're very versatile organisms that have a lot of different applications, and we're just now starting to crack the surface of what we can do with engineering with these organisms. So I hope that answers your question. It's a little bit long-winded for you.
No, that was perfect, Kyle. Thank you. So these are from your booth inside, right?
That's correct. So you'll see these flasks at our booth inside. This is an alga called Chlamydomonas reinhardtii. It's been a model organism since the 1940s. And this is an unknown species of green algae which has been isolated from the Red Sea and we're just starting to work with. So obviously being here at KAUST, we're very interested in working with organisms that grow in salt water, especially local ones that come from the Red Sea, because the Red Sea has higher concentrations of salt than in other oceans or water bodies around the world. So the ones that we find here are much hardier, they're much more adapted to the local climate. But we've even found in our bioreactors, which are fancy flasks that we use to control environment, that even this alga from a farmer's field can grow in local Saudi conditions. So we're seeing what we can do with these organisms in a local context here to convert carbon dioxide into valuable products.
Okay.
Yeah.
And you said this one is unknown.
It's unknown at the moment. We are not entirely sure what species it is. So they're both green, which means that they come from a similar lineage of organisms that shares an ancestor with all of the plants that you see out in your garden right now. But we haven't sequenced it yet, so we don't actually know exactly what species it is. And that's something that we can do here, of course, with the help of the Biosciences Core Labs and their sequencing facilities, and all of the collaborative work we can do at KAUST. So.
And does it mean you get to name it?
I'm sure somebody has already named it. That's the problem with working in biology. There's always somebody who's named something first, even if they didn't know what it is. But maybe. And then we'll call it Kaustiensis or something, KAUST Latin name. It's more important than my name, that's for sure.
Very nice. That sounds good.
Yeah.
Well, let us know. Please come back and give us an update when you find out what this unknown creature is.
Of course, we will.
Thank
certainly.
you so much, Kyle,
You're
and
welcome.
hope you enjoy the week. Thanks for taking some time to talk with us today.
Absolutely. More than happy to. Thanks, Carolyn.
Thank you.
Bye.
Bye. Welcome back. Now I have with me Kazuhiro Okawa, Professor of Electrical Engineering. Welcome, Professor.
Nice to meet you.
Thank you for coming and sharing some time to talk with us about your research.
Yeah.
You have a booth here and you're sharing some interesting information with us about LEDs.
Yes.
I know LEDs are in my phone, I know they're on the TV screen. Why is this connected to sustainability? Maybe give us a little scope about LEDs and your work, and then tell us how that relates to sustainability.
Yeah. So strong point of LED is energy saving. So we can save energy. But the current mobile use liquid crystal display, and the backlight is white LED.
Okay.
But we are developing tiny LEDs, so-called micro LEDs. So using that RGB LED, green, three primary colors, red, green, and blue RGB LED will be forms of pixels. So using that, so we can save energy very lot. Because in case of white LED, so white LED backlight and some instruments and the liquid crystal and another instrument, so intensity light getting weaker. So LCD is very energy efficient compared to cathode ray tube or the display. But so future display, so-called micro LED display, is also quite big jump, save energy.
Okay.
So therefore, you can charge your mobile once a week in the future.
Which would be amazing. Right now it's twice a day, I think.
Yeah.
And I'm not on the phone all the time, but it just eats a lot of battery. So it constantly needs charging, or you have to carry now an extra battery case to be charging the phone all the time if you're in travel or in transit. So once a week would be fabulous.
Yes.
And this is because of, so you say we have the blue and we have the green.
Yes.
But it's the red.
Yeah, but if you check the traffic signal, there is a bright red LED.
Yeah.
But that material is difficult to make a tiny one. So decreasing the size, efficiency of that drop down. So that material is not available for new display.
Okay.
But we're trying to develop different, challenging different material. So-called nitride semiconductors. And at KAUST, we can grow this semiconductor by ourselves. And using core laboratory, we can make tiny devices. So from we can make this LED from scratch at KAUST.
You said grow.
Grow.
You're growing them.
Yeah.
It's not a term, a verb I usually associate with electronics, but why do you call it grow?
So at the beginning, there's only substrate, nothing on that. And we control the atomic steps and control the atomic level, and can make a very precise control semiconductor structure. And using that, we have achieved high brightness LED LEDs in the world. So LED LEDs is a missing part of micro LED display. Of course, current LED LED is a world record, but not enough yet.
Okay.
We would challenge one order more and keep the world record.
Okay, sounds good. Looking forward to keep us posted if you
Yes.
when you succeed yourself.
Yeah, of course.
And you have a booth inside. If we take a look at the booth, what will we see? What have you got there on display?
Yeah, we are showing a micro LED itself, but micro LED is very tiny. So if you look at the naked eye, just 1 point. But we set a microscope. Through the microscope, you would recognize. Looks 1 point, but there are 100 LEDs on there.
So I can only see one if I look with my
Yes.
eye, but under the microscope, then there will be 100.
So if your eye is a microscope, you can recognize. But maybe your eyes normal eye.
Yeah.
So you can see micro LED.
Wow, that sounds exciting. I'm going to go and have a look at it.
Yes, please.
Okay, thank you so much for joining us, Professor Kasu, and keep us posted on how your research updates.
Thank you very much, and welcome to our booth. Thank you very much.
Thank you.
Good afternoon, and welcome back for today's last session of Crow Talks here in the auditorium. My name is Sara Dorini, and I am a scientific editor in the research communication team in the Office of the Vice President of Research. I'm very glad to introduce our first speaker, Professor Susana Nunes. He is Professor of Chemical and Environmental Science and Engineering and Vice Provost for Faculty and Academic Affairs at KAUST. She started her career in Brazil, where she got a PhD in chemistry from the University of Campinas. Then she moved to Germany as Humboldt postdoc fellow in polymer physical chemistry at the Johannes Gutenberg University in Mainz. Then she moved as visiting scientist, and she worked at the Max Planck Institute for Polymer Science in Germany and then in Tokyo Institute of Technology. She's a fellow of the Royal Society of Chemistry in UK and of the Sao Paulo Academy of Science in Brazil. She has decades of experience on polymeric membrane development with more than 270 publications in the field, 7 books, and several patents. In Germany, she was head of the Department of Membranes for Sustainability Energy at Helmholtz Association. At KAUST, her lab continued to focus on new polymeric materials and their translation into membranes for liquid, gas, and vapor separation. Please welcome our first guest.
Okay, thank you very much for the introduction, very kind. I will give you an overview on membranes, on polymeric membranes, where sustainability can profit from membranes, and a flavor of what we are doing in our lab. This is not only my lab that's doing polymer membranes here at KAUST. We have a very good group on that. So here, first, we are in a transition, in a time of transition. And I think we all agree that the future has to be sustainable. And we see, with all the discussions that we had in the last months, even more and more, and also here at KAUST this week, we see that we are going to a green future where green hydrogen technology will hopefully dominate. We will have solar and all kinds of renewables, biorefineries, having zero waste, and so. But this is a long way to go, and this time of transitions is becoming shorter and shorter. And in all these points, we have a lot of opportunities for membranes. Some of them are reality, some of them are already there for a while. For instance, reverse osmosis is now the most important way of desalination. It was thermal when I arrived here in many parts of the country. Refineries with capture of CO2, so this are already being done, or having coal plants with some capture of CO2. But where we can really use membranes, where it makes sense, it's not only about having the feasibility in terms of material that is there, but we need to choose points where the energetic balance makes sense also. It doesn't matter if I have a super material, and then to use that, I need another plant to move that separation. So as a whole, you have probably heard that about 15% of the energy consumption all over the world is used for separation, in different kinds of separation, in a general way. For CO2 separation, for instance, you could use the CO2 for reducing the footprint for coal plants or refineries, or you can use for separating CO2 from methane in natural gas. An important application is in cement industry, where CO2 is a lot of CO2 being produced. But in this case, even if you use renewable, you still have the CO2 coming from the material itself, for carbonate, so that you really eliminate. So 2/3 of the CO2 in this industry is coming from the material itself. But in the future, we might have new methods, even for the cement industry, that will not require the separation itself. I think that there's other ways also to apply membranes, and some of them are reality. And of course, hydrogen technology is getting more and more important. But today, 95% of the hydrogen is still coming from fossil fuels. I think we are in the discussion, and not only discussion, we'll be implementing new ways to produce hydrogen, but we still are depending on fossil fuels. And refineries, you can make the refiner more sustainable. You can use, you can recover hydrocarbons, you can recover monomers in the chemical industry, and all of that is being already done by membranes. This is all commercial. Of course, you can produce membranes much better, more effective, more selective, but there's a lot already reality that maybe many of you don't know yet. So reverse osmosis, again I mentioned, is already a really well-established application of membrane. But I think the future really is to use membranes for many of the technology that we are considering sustainable, future sustainability. Hydrogen technology, electrolysis, for the electrolysis, the core part of the electrolyzer is a membrane, it's an ion exchange membrane. Seawater desalination, where you can not only reject all the salt and have drinking water, but to separate ions, and maybe perhaps use part of these ions. Zero emissions, zero waste, so to use membranes to really recycle not only water, but solvents in the chemical industry. I think the future of the chemical industry is being more sustainable, is being used, integrate different processes in a more effective way, not only for environmental reasons, but to be more effective, to be more economically more effective, with more attractive for many of us. Biorefineries, I think, is also something considered in the future. And we are here in a region where it's very warm, and then air conditioning is essential to use, and dehumidification and other kinds of actions. And the production of the membrane itself has to be more sustainable. It's a lot of solvent process that we have to make it greener. In my group, and not only my group, but in what we focus is, maybe I can summarize in three main topics. One is to develop membranes with higher stability, higher thermal and solvent stability, so that we can use membranes in the chemical industry more than we use today for water application. So in that sense, really high performance polymers, cross-linking, thermal treatment for cross-linking, or high selectivity. If we want to use membranes in process which will be more effective, in process that separations that cannot be done today in a few steps. There are many processes in the pharmaceutical industry where you have a lot of different processes to get a product at the end. So if we can substitute many of them and reduce the amount of steps, we are also gaining in terms of sustainability. In these ways, we use different functional building blocks to prepare membranes. And we work also under the sustainability of the membrane manufacture itself. All we do, we have to consider scalability. So that means it's not enough if we have an excellent material, excellent way to prepare a membrane, if we cannot bring that to, at least in a technical way, in a way that we can have the perspective of bringing that in the industrial application later on. And applications, we work with different ones. Nanofiltration, I think, is one of the main applications we work with, but I have been working with gas before KAUST and have some work on gas now, and ion separation and so on. What kind of approach we use for membrane fabrication? So if you see here in the bottom, you see different size. This reverse osmosis, nanofiltration, ultrafiltration, microfiltration is increasing the size of the pores that we use, and these are required in different applications. So like gas separation on reverse osmosis, you practically I don't know, it's controversial if you talk about pores or not. So it's very dense membrane, and so on, you get that. And for different ranges of pores, so you can use different methods to prepare the membrane. For instance, the most common way to prepare membrane is what we call phase inversion. So you just have a solution of a polymer solution, and then you cast the solution on a support, and you immerse in water mostly, and almost by magic, not magic, but thermodynamic, you get a membrane with a controlled pore size. So these, the improvements that we need are greener solvents or have a better or narrow pore size distribution, more stable ones. Or there's another method that we use many times in desalination or interfacial polymerization, the thin film composite membranes. So you know, as thinner the selective layer, less resistance we will have for the transport of water or the solvent. So that means we have to have the layer that will really bring the highest resistance has to be as thin as possible. And this is a classical method. I will show some examples. Good. And let me show you some of the examples that we work. First, with the membranes for high-performance polymers for different applications. So these polymers, polytriazole, we are looking for polymers that are much more stable than the regular ones. And we will find, so we find polymers that are stable as high as 500 degrees, which is, then includes application in chemical industry that are not really considered today. So we can use with polymers, the big advantage is that we can process very well in continuous machining. So then if we have materials that are resistant, so then we should look for them. And this is one of them that we have been working. And if you see in the bottom, so here's practically a cut across the membrane, and on the top is just the surface of the membrane. And by choosing different solvents, we can completely change the morphology, not only change the environmental impact. We work with these polymers for very long and different applications. This is a recent paper where we work with the gas separation. And this, in this case, is separation of CO2 and methane. And you see, I think for those who are from the field, if you see that plot on the right, you want your membrane to be as far on the top or not. This is just the first step, and then from that, you need to have the membrane prepared in a really technical way. For nanofiltration, so in solvent, if you use in solvent, in process of separation using solvent, you need polymers that are very stable, that will not dissolve in as you expose the solvent. But if they are so stable, it's hard to process, it's hard to dissolve and process as a membrane. So what we do is we modify these polymers, commercial polymers like PEEK, polyether ether ketone. We make them soluble, we prepare the membrane, and we recover, we regenerate the original insoluble polymer. Or this is actually quite old, let me go for the next one. This is quite old slide for before KAUST on hydrogen technology. I work a long time with the fuel cell. So fuel cell, you have challenges like for transport, you want to have a polymer or a membrane that works even at temperatures above 100 degrees and at low humidity, because in this way you can tune the process in the car. So if you use in the car, you want to tune the conditions not so far than what you use today for combustion motors. And in this way, we have been working with polytriazole again, functionalized with the sulfonic groups. For, again, the interfacial polymerization. So this is what I mean, the best method if you want to have a very thin selective layer for different applications is the method that you use in most membranes in desalination today, But this is a method that can be extended also for other kinds of membranes, also for solvent-resistant ones. So the idea is, I don't have a pointer here, but if you see the first picture there, you see two separations, like oil and water. So and if you have monomers that one just dissolve in the water and the other just dissolve in the oily solvent, so they will only mix in the interface and only react in the interface. Once you form that layer, nothing more will react. So you have a very thin layer, and you can promote this reaction on a support. So this is then the way to prepare membranes for that. And most, of course, the membranes used for desalination, they are hydrophilic membranes. They use for water. So if we want to use for solvents, so for like toluene or so, you need to use a different chemistry. This is a recent paper with a group of Professor Sekeli here at KAUST, where we use fluorinated groups for that. Or I mentioned also using building blocks, and about if we could use preformed pores. Let's say if we could use cyclic molecules that will, at the end, give the selectivity of your membrane. So this is a concept that we have been working with other groups at KAUST. In this case here, the first slide, cyclodextrin with fully cross-linked that by interfacial polymerization, and we can have a membrane at the end that even separates molecules of the same size by shapes. So in the range of nanofiltration, 300, 400 grams per mole, in the size of really relatively small molecules. Or this one, instead of having the circular building block, we have a triangle as a building block. This is another one with the collaboration with Nivin Kashab. So here, if we use this building block, it's not only the size selective, but this chiral. You know, chiral is if you have molecules that have a mirror image of each other. They are exactly the same chemistry, same size, but just the mirror image. So they are not the same. You cannot put them this way. And this separate then is very important in pharmaceutical industry, because many of the medicines also, they are, you might have in one isomer the perfect activity, and the other one you cause a lot of problems. Like I just saw this week is about 60 years of the Contagen. What is in my generation, grew up with many kids. We had problems because of medicine given to their mother when they were still pregnant. So this is a typical example of how chiral is important. So artificial water channels, the separation of water using different ways, different channels, creating channels that are inspired by biological molecules. So this is a work together with Professor Babouin in France. So he has assembly of imidazole channels or imidazole molecules forming a channel, and we integrate in interfacial polymerization. Or this is another way to also interfacial polymerization, but where we grow a network, a very controlled network, which is, this case is called covalent organic network. In this paper here, it's more a fundamental paper, but we use segments that are sensitive to light. So they open and close. It's like you open and close the membrane with by inserting the right light wavelength. So again, as I mentioned, everything that we propose, so at least we try to use concepts that we could transform, translate into a machine and so on. And that's a kind of machine that we use to prepare membranes, not only in a 1 per 1 centimeter of membrane, but really in a continuous way that you can really use to prepare modules out of that. So this is for flat sheet membrane and also for interfacial polymerization to have it in a machine. And also what we call hollow fiber. Hollow fiber, many of the membranes are prepared in the form of hollow fiber because it's more effective in packing. So like the area per volume of membrane, it's much higher. So in this case, we have a machine, a continuous machine to produce hollow fiber in our lab, and then we can, it's like kind of extrusion, of a solution extrusion. And then we can pack the membrane, which you see here in the middle is a cross-section of this membrane. You see that's quite well porous, and in the middle you can really circulate the feed or the permeate, as depending on the method. And you integrate in models. We use that. I think we had one of my co-workers talking this morning. There's another one in a couple of days talking. Is part of the project that we have in the cooling initiative at KAUST. So to work with dehumidifiers, to prepare dehumidifiers for integration in air conditioning or in other applications. So in this case, we have the hollow fiber membranes packed, and then we coat it with different chemistries, and which are preferentially permeable to water. So that means we have a water vapor going through, and really the nitrogen or the air is dehumidified. So just 2 less slides. So that, again, everything, I think I could say, we will agree that membranes are more sustainable than thermal separation methods in most of the case. But the membrane preparation itself has to be more sustainable. So that means we work also on substituting some of the solvents that we use, because it's basically a solvent process. And in Europe especially, there are many discussions on which solvents will be really acceptable, or which one will be banned or will be reduced. So we have to be prepared, and I know that many of the membrane companies are thinking on that, but this optimization for decades will not be substituted in just from one day to the other. We have to be prepared and use solvents that are less toxic than what we have today. Or recycled polymers, or having polymers that we synthesize and the polymer itself will be cycled in the different ways. This is, I think, it's part of the polymer development nowadays. I think polymers got a bad name because microplastics and so on, but we still need plastics for a long time, and I think it's important to propose polymers which are more sustainable in itself. Good. In summary, the conclusion of this talk is there's a lot, the technology, membrane technology in many cases is already available, and it's already contributed for this transition of more sustainable. But we have, of course, to always to consider as a whole how much we gain in terms of sustainability if we don't propose something that will use much more energy for the separation than before. And I believe one way to use membrane is really to, in the chemical industry, to have the whole industry more sustainable, not only to capture the CO2, but to avoid the elimination of CO2 and work in process that you can have the whole industry more sustainable. And of course, always think about scalability if you are trying a new process. Then I want to thank all my group. This is a relatively recent picture of the group, and KAUST for everything, for the support and the opportunity of being here and contributing, hopefully, for a more sustainable future. That's it. Thank you.
Thank you very much, Susanna. This is a small gift for you.
Oh, thank you very much.
For the nice talk. I think we have a few times, Susanna, if you want to stay here a few minutes for some questions, perhaps, from the audience. Okay, yes, one question.
Okay.
Good afternoon, Doctor. Thank you for quite informative, very technical for me. Mohammed Ramadan, Yasin Agri. What future you see the reverse osmosis? Is it continuous? Is it gonna continue to be the right way of doing desalination?
I think so. I think this is if you compare with any other available method today, I think this is the most effective one. I think it's only you have to be more sustainable in the energy that you use for the desalination, for the reverse osmosis. You might find other ways. I think there are a lot of other ways being discussed, but for now, I think reverse osmosis is quite optimized for decades and continues to be quite effective. I think for the drinking water, if you use renewable, I think it's a good way. So there are other ways. There are, I think, other challenges if you want not only to have the drinking water, but if you want to use the brine, or if you want to use the ions in different ways, if you want to separate them, there's still challenge. I think it's still a lot to do with that, but it's still reverse osmosis together with other, maybe also other membrane processes.
Thank you.
Yeah.
Thank you so much, Doctor, for this nice presentation. I'm Adil Bushnak from Saudi Aramco. My question is, as you know, we are now into the sustainability and moving to renewables and hydrogen fuels. How do you see the reverse osmosis technology transfer to industrial scale?
The reverse osmosis transfer to other applications, to
industrial scale.
Reverse osmosis is industrial scale for long, so in water.
No, I mean in terms of the current concept.
The current concept of reverse osmosis extended to chemical industry.
Exactly.
Yeah, I think this is it's feasible. Of course, it's feasible. There are like nanofiltration, which is like very causing of reverse osmosis that is used just a little bit more open membrane. This is being used in large scale already. With I know there's a company that I know very well working on 20 tons per hour of hydrocarbons of separation together with the petrochemical industry. So this is already happening. So this is not research, this is really working. And I think depending on the kind of process or separation that I think that's very feasible. Sorry.
Maybe I was not that clear.
Yeah.
I'm talking about as we speak now.
Yeah.
What do you anticipate reverse osmosis to grow in what way the growth is?
Yeah, well, for water, I'm pretty sure that will continue for long to be the method for desalination and for drinking water. I think there will be more options for if we have membranes which are more selective, not only rejecting everything, all the salt, but have differentiation between ions. I think this will be also used in the future, and this for water. And for chemical industry or for this will be also more and more used. I think it is a question of having membranes that are stable. You need membranes that will not, so most of the membranes that we use for desalination, they are stable in water. They are stable in a temperature that may be 100 degrees or so. But in many other cases, in the process in chemical industry, separating, I don't know, catalysts, separating some solvents, purifying solvents, or different other separations where you do it in an organic solvent. So you need something more stable. And there are membranes already, better membranes available with higher stability. We need more, but we have already in the industry. And I think as we grow, as we move in terms of being more sustainable, there will be more options for that. I think, especially in Saudi Arabia, you know, if you are in a country which is a specific industry is very stable, and they're working for that with a traditional separation method for decades, it's hard to change. But if you build a new plant for whatever, so if you want to build a new plant and in a growing society, growing industrial really situation like we are here, then we should start from the beginning thinking about solutions that are more sustainable. So, and I think it's a special situation where you really can use methods that are accepted as sustainable, and you don't need to, you are not paying the price for completely substituting something that's working well. So if you build a new plant, you should consider having something that is, will be not only because of the environment itself, but it's more effective, that will be more economically effective also. Yeah. Any more questions? Yes.
There is another question.
I'm going to ask a chemistry question.
Yes, please.
Since you guys have been talking about reverse osmosis. The trianguline.
Yeah.
How do you control this? Because from like thermodynamically speaking, it's tough for these molecules to come in a triangular shape. I would assume it will.
That is not stable. There is more tension there. No?
Yeah, exactly.
Yeah.
So how do you control that? And then once you control that, can you also control the size of that as well?
In principle, yes. Yeah, in principle, you can have a larger triangular mean or a smaller.
Just by controlling the concentration of the monomer, or like how?
Yeah, but the size. So this is produced. So who produces the triangular mean is the Wien's group. But in principle, they use segments which are reacted together. So if you want a larger triangular mean, you have to use a segment which has a larger spacer.
Why it doesn't go this way instead of like closing up?
Why the reaction forms the triangular mean and not?
Yeah.
I don't know. You have to ask her. But
because
this
thermodynamic speaking, it just doesn't make sense to me.
No, but depends on I don't know the kinetics of the reaction myself in this specific case, but it's I think it is quite demonstrated that it works in this way. And what we use is we functionalize that. Once it's formed, that we know that it's a stable one, we have a functionalization that will help us to cross-link, to polymerize.
Have you tried this with something else, or like this is the
with cyclodextrin, for instance.
Same thing.
And we are working with other monomers also. Yeah.
Thank you.
Yes, please. Yeah.
Thank you very much for such a nice and interesting presentation. I would like to ask a question regarding, like, we can see how many great advances have been there in the membranes field, but that there is still a gap between the research and the advances in research and the actual application in industry. I would like to ask you what you think that researchers should do in order to, or if there is something we can do to foster the implementation of these new technologies in industry, or it's completely up to other people.
Oh, I think we have a translation of grants at KAUST. We have the opportunity of working on continuous machines, and so that's one step forward. I think if you want to discuss the further application or implementation, you need to provide a solution that is scalable, that you can at least produce in meters and meters and meters, and demonstrate that you can do that. From that to having in an industry producing your membrane and not the polymers that they're using for long is also a long step, because they have other restrictions that even the solvents they have to have the authorization to use a different solvent. It's more complicated that we are used to. But I think once you have a demonstration in a larger scale and you work together with the industry, I think that's the way to go. So it's, but it's not easy, I know. Yeah.
Thank you very much again, Susanna. I think that now it's time for our second speaker of the session, Professor Javier Ruiz-Martinez. Professor Ruiz-Martinez started his career with a PhD cum laude from University of Alicante. Then he moved to Utrecht University, first as postdoctoral fellow and then as an assistant professor in situ spectroscopy. After this period, Professor Ruiz Martinez moved to from academia to industry and joined the Process Technology Department in AkzoNobel as heterogeneous catalysis specialist. In 2019, he moved back to academia as a faculty member of the KAUST Catalysis Center. During his academic career, he authored multiple papers in renowned journals such as Nature Chemistry, Angewandte Chemie, and Chemical Reviews. He was awarded of the prestigious Veni Award from Dutch Research Council and Young Scientist Prize Award from the International Association of Catalysis Societies. In KAUST, Professor Ruiz Martinez Group aims to understand the structural properties of catalysts during synthesis and when working under real conditions. Particularly, he develops novel spectroscopic tools and their application in industrially relevant processes and model catalysts with well-defined porosity and reactive center. Please welcome Professor Javier Ruiz Martinez.
Thank you. Thank you so much, Sarah, for the kind introduction, and good afternoon, everyone. It's my great pleasure to be here today to talk a little bit about our activities in my group here at KAUST related to sustainability. And what I'm going to do today is I'm going to show you a specific case in which we are trying to resolve this problem of NOx emissions from automobiles, from mobile applications. And I'm going to show you how we can understand the structure of these materials by using different type of techniques. And there we are trying to unravel one of the unsolved questions in this chemistry, in which there have been quite a lot of controversy and many theories to understand what is cerium doing in this beautiful catalyst based on manganese. And I would like to start my presentation today by showing this image here. And this image is a clear example of acid rain. And acid rain is one of the, it's basically rain which has a high acidity. And that high acidity is damaging, for example, forests, but also life in water ecosystems. And also, for example, they are damaging even buildings in our cities. And there are many very recent studies which says that this acid rain is also part of the cause of these landslidings in China that is happening. So you can imagine that globally it's extremely important, this type of events. So this has happened since the beginning of the Industrial Revolution. And that's happening because we are massively using and burning fossil fuels. And those fossil fuels contain sulfur components that are creating, after combining with water, some acidic molecules. So these sulfur oxides, but also these nitric oxides, are creating those acids that are falling after the rain, and therefore creating all these damages. So the scientific community started to put a lot of attention on that in the 1960s. So this is really happening over centuries, but the scientific community started putting a lot of emphasis on the 1960s. And only in the 1970s, policymakers start to making some actions, started to resonate what was happening, and trying to put some legislation in action in order to reduce the emissions of these sulfur oxides and nitric oxides. And since then, many, many advances have happening, and we have been able to decrease the damage of this acid rain and decrease the emissions of these sulfur oxides and nitrogen oxides. But still, it's very often to see in many of our cities today these images here, which are basically caused by the combustion of fuel by our vehicle, by our cars, which are creating this emission of, more specifically, nitric oxides. And what I want to say is that even if we have the cleanest fuel and the greenest fuel, we won't be able to reduce the emission of nitric oxides, because those emissions are coming from the contact of oxygen and nitrogen with the high temperatures in the engine. So no matter how clean is our fuel, we will always have emissions of nitric oxide. And this is a misconception that many people see, that they believe that if we have clean fuels, we can reduce the emissions of these toxic gases, but it's not true. So we have to take action, and we have to start putting some measures into this. But what I mentioned to you is that this type of nitric oxides have effects on the ecosystem, but they also have severe effects on humans. And you can see here several pathologies that might suffer if you are exposed to these nitric oxides. So it's very clear that we have to get rid of those. And here I show you a pie chart in which you can see the emissions depending on the different industries. And you can clearly see that road transportation accounts for around 40% of this type of emissions. So if we are able to have a technology reducing those, we will make a very good impact on the reduction of those nitric oxide emissions. So as I also mentioned to you, policymakers have seen that, and there are more and more stringent legislations which are trying to reduce the emissions of those, NOx gases. You can see here, for example, two examples from legislations in China and the European Union. And you can see, for example, in the one on the right side, that the restrictions are more and more stringent. So we are trying to reduce as much as possible these emissions of toxic gases. So we have tried to solve this problem from chemistry, more specifically from catalysis. And nowadays what we have are substances, catalyst materials, which are able to take this nitrogen oxide, which is there at the bottom, and combined with ammonia and oxygen, we are able to convert them into nitrogen and water, which are completely harmless. So we already have the technology to do that. And actually, we are implementing those in our heavy-duty trucks, as you can see here. So we have this very beautiful catalyst called copper chabasites, which are doing the job. But as you can see here, these materials are very efficient at temperatures around 200 degrees C and higher. But there is a problem, because when we start our car, the exhaust is very cold, and therefore we have a lot of emissions at that moment. And it's so important that you can see here in these reports that the low temperatures emissions are accounting for around 70% of the total emissions in a vehicle. So there is still some room to work on that, and we really have to work hard on trying to find a way to mitigate those emissions. So in our lab here at KAUST, we tried to also see that, and we were testing this copper zeolite catalyst, which is available for these heavy-duty trucks in reality. And what we could see and verified is what they were mentioning in the reports. So when we have a high temperature, you can see how these catalyst materials were able to convert around 100% of the NOx emissions in a truck engine. However, when we were going to temperatures lower to 200 degrees, you can clearly see how the conversion drops, and then the catalyst is not working efficiently. Here at KAUST, what we are working is in manganese-based catalysts, which are extremely active, and you can see here that at very low temperatures, we can get activity 4 times higher than the commercial copper chabasite catalyst. So we believe that these are very important and very promising catalysts that we would like to investigate. So the first thing that you do when you want to investigate a new material is to see what is reported already in the literature. And what we observe is that there are many reports on this type of catalyst, and we were very interested to understand what is the effect of cerium in this manganese catalyst, because it was always used in these formulations, and it was disclosed that they were increasing the activity of these materials. So while going through all these type of publications, what we observed is that they were claiming this promotional effect of cerium by this redox mechanism, in which the cerium oxides were helping the manganese to reactivate the active sites, and therefore the activity was much higher. There were other reports also explaining that this cerium was absorbing more of the toxic gases and therefore converting them more, and also about the structural properties of cerium. What you can clearly see in the literature is that there is no a general consensus of what is the role of these cerium oxides in the reaction. So that was the main motivation of our work, and therefore we'll try to unravel what's the role of this cerium oxide in order to try to make a much more rational design of catalyst. So to do so, what we did is basically do a very thorough systematic synthesis of materials, of manganese-based catalysts composed of titanium and cerium. And then we synthesized over 30%, over 30 catalysts, so really a wide range. And we look at into different compositions. And after the synthesis, we were characterizing the materials just to see what is the structure and what are also the active sites of those materials. So after the synthesis of this material, we just basically tested under real reaction conditions, so under conditions that happen in a real combustion engine. And what we observed is that when we found out a range, an area which is there in green, in which we have a high conversion level. So it seems, and if you can see, that area corresponds to materials which contain a little bit of cerium oxide. So it seems that the good catalytic performance is observed when you add a little bit of cerium, okay? But this is just purely catalytic performance, so we wanted to understand what is the structure of those materials when you add this cerium oxide. So for that, we did a battery of characterization, and here you can see on the left side the crystallinity of the different materials after synthesis. And you can see, if we focus on the bottom line, you can see that when we add a little bit of cerium oxide to our catalyst formulation, we develop an amorphous material. And if you look at on the right side, which is showing the surface area of the materials synthesized, you can see also that this amorphous area observed on the left side corresponds to a high increase in the surface area of the catalyst, which tells us that when we have this amorphous type of phases, we have a higher surface area, and if we have a higher surface area, we have much more active sites exposed on the material, and therefore we have a high chance to have much more reactivity, so reduction of the NOx emissions. So this was the characterization of the structural characterization of the materials, but we also wanted to look into the structure at the nanoscopic level. And here you can see some electron microscopy images of the manganese titanium oxide. And what you can see here is that this type of materials have a crystalline structure. So those fringes resemble a crystalline structure which is coming from the rutile titanium structure. And surrounded by this crystalline structure, you can see an amorphous layer of manganese, which was also verified by this elemental analysis of the bottom, in which you can see that the core of the catalyst particles are pure titania, and on the surface you have a layer of amorphous manganese oxide. So that was the structure of these binary materials. But when we add the cerium, something happened completely. So there's a huge change in the structure of the material. So the first observation is that you don't see anymore any crystalline structure, so the material becomes completely amorphous. And if you look at it into the elemental composition on the right side, you can see that now the different mixed oxides are very well mixed. So you can see that there is a complete difference in the structure when we add this cerium oxide, and now the different metal oxides are very well mixed. We also wanted to understand the chemistry of manganese after adding cerium oxide, and to do that we did a method called hydrogen TPR, in which we are looking at the temperature when the manganese oxide is reducing. And by looking into that, we can understand how are the redox properties and therefore the active sites changing by the addition of cerium. On the left side, you can see the catalyst material with a low manganese content, and you can see in this what you can see is that when we increase the amount of manganese oxide, the cerium oxide reduction goes to lower temperatures. So we are definitely, the manganese is definitely interacting with cerium oxide in the catalyst formulation. If we look at to the right side, what we can see is that when we have a low cerium content, is that when the catalysts do not contain any cerium, those two lines at the bottom, you have two reduction peaks which are corresponding to the reduction of manganese oxide. But as soon as you put a little bit of cerium in the formulation, you start seeing how the reduction of manganese goes to higher temperatures, which is telling us that the cerium oxide is interacting in close proximity with manganese and somehow is changing the redox properties of that material. So with all this characterization, we have here endeavored the structure of our materials, in which on the left side, we have the manganese titanium oxides, which is composed of a crystalline titanium, and on the top, we have an amorphous layer of manganese. But when we add a little bit of cerium oxide, the structure change completely, goes to amorphous, and now we have a well-mixed and a homogeneously dispersed mixed oxides. So that was related to the structure of the materials. Then we wanted to understand the activity of those. And here what you can see is a plot in which we are looking into the activity as a function of the manganese content of the catalyst. So we are looking at how much NO these catalysts are reducing, so are converting. And what we can observe is that there is a modest correlation of the activity with the increase in the manganese content up to around 60%. And then we can see how the activity is dropping. So what this tells us is that the manganese is somehow directly related to the activity of the material, but there's something else happening. So there's something else which is playing a role in this type of reaction. So what we did now, because the cerium was increasing the surface area of our materials, we were normalizing this activity with the surface area. And here you can see the plot after doing this normalization. And the red dots are the binary manganese titanium oxides. And you can see that the activity now is directly related to the manganese content. And in the blue dots, you can see that the catalyst containing also cerium. And what you can observe is that there's also the same tendency. So activity increases with the manganese content. But in this case, the intrinsic activity of the manganese species is much lower compared to the binary. So what we are observing is that the cerium oxide is creating manganese uptick size with lower activity, which is really against what we were observing in the previous reports. So what we are seeing is that actually cerium oxide is a pure structural promoter and is not promoting the activity of the manganese oxides in the catalyst. So to make this hypothesis stronger, what we did is exactly the same methodology for the previously reported papers, and we normalized them to surface area, and we observed very similar results. So it seems that our results and the literature results are consistent, and actually cerium oxide is a pure structural promoter and is not, and it doesn't help into the redox properties of the manganese as previously described. We also look into the activity to N2O, which is a side product that can be produced during this reaction. And we also observe that there is a higher than one order relationship of the N2O rates with the manganese surface density, which tends to believe that it seems that the cerium oxide is somehow interacting with the manganese species and therefore reducing the formation of N2O. Most likely because we have less redox active sites in close proximity. So with all those results in hand, we were also foreseeing the reaction mechanism for this N2O selectivity, in which we can see that when we have manganese titanium oxides, we have the reaction of NO with these manganese oxides, and because we need two consecutive active sites, then we can form the N2O, whereas when we have a mixed oxide with manganese, cerium, and titanium, the active sites are far apart each other, and therefore we are reducing the two-step oxidation to the formation of N2O. With all this, I would like to thank our sponsor, which is Umicore, more specifically Fei and Lutz. And of course, KAUST. I would like to really thank Lieven, Linga, and Amin, which were strongly related to this work. Also Sami for the electron microscopy work, Pasi for the diffraction measurements, and also Najib from Core Labs for the XPS data. And I would like to thank you all for your attention, and I'll be happy to take any question that you might have. Thanks. Thanks.
Okay, so we have a few minutes for a few questions, if anybody from the audience. Okay, then I will ask a quick question. It's more a curiosity that can also connect with the last question that was asked to Professor Nunes. Sorry. Sorry. So it's a question that is connected to the last question that was asked to Professor Nunes. You have experience both in doing research in academia and in industry as well. So maybe you can also give us your opinion about this gap that there is sometimes between academia and industry.
Yes. Yeah, I think I truly believe that a very strong collaboration with industry and academia is always beneficial if you want to translate your technology to reality. And I've seen that during my experience in the Netherlands, in which we had a very close connection of the universities and industry, and that helped a lot to really develop new technology. So I think really a close collaboration in that respect it's always very useful. And for example, what we have observed here, these type of materials are very easily scalable. So we always try to do these materials in order to have a potential to be translated soon to a real commercialization.
Okay. So yeah. You keep always in mind the potential of having industrial application when you're doing your research.
Yeah, definitely. So of course, I mean, this industrial, so that's very important, although we also don't have to forget about the fundamentals. And sometimes you have to develop very fancy and very expensive materials just to try to understand how those work. And afterwards, then you can try to make something much cheaper which can be translated. So they don't have to be opposed. So I think that could be also a different step during the pursuit of a better material.
Okay. Thank you very much. Is there any question from the audience? Yes, one.
Thanks, Javier. Great presentation. Just with the upcoming Formula One, is any of this research going to be applied in any of the F1 cars moving forward?
Could you repeat your question?
Sorry,
please?
just with the upcoming Formula One, in terms of the catalyst, is any of your research going to be applied in the Formula One industry? I know you mentioned obviously with the trucks.
Actually, that's a very good question. To be honest with you, I have no clue. I don't think those cars, they have a NOx abatement system. But I will really look into that. That's a really good question. Thank you.
Okay, if there are no other questions, then I want to thank again both our speakers. Oh, there is another question? Okay, sorry.
Yeah.
Thank you, Doctor, for this presentation. Just short question. How do you foresee the commercialization of this catalyst?
Yes. What we have obtained so far are very promising results, and we are making major advances on understanding how these materials work. But this, I mean, to be honest with you, we still have some work to do in the sense of how stable are those materials under real conditions. And there we are facing some issues that we are currently investigating. For example, these type of materials are extremely sensitive to SO2 emissions. And during the combustion of the fuel, a little bit of sulfur dioxide is formed, and that's somehow sticking very strongly to the material and deactivating it. So we are currently developing some technologies to get rid of that SO2. And if we manage to do that, there will be high chances to commercialize this.
Okay, I think that's the end for today. Thank you again to our two speakers. Thank you to the audience on live stream. And stay tuned for the next talk in the next day. Thank you very much.